right? If we add a really big number, like 2,000 plus 0004, here's something that you need to appreciate. The impact of significant figures, and why we care about significant figures, is because we're wanting to maintain a certain degree of accuracy. So, remember when we looked up the distance between the Earth and the Moon? Right? And we were given a number that had a lot of zeros on the end of it, a certain number of million miles. Well, let's say that I was asking you to add the distance between the Moon and the rock I just threw off of the surface of the Moon. Would that be a meaningful difference between those two numbers? Even if I could measure accurately how far I threw that rock, because that 0.0008 or that 0.0004, the fact that we can measure that small means I have a very accurate yardstick, right? But just think of it in terms of scale. Is that much of a difference going to matter if the number I'm adding it to is 2,000? No. So the fact that we lose all of those things when we add this for significant figures, adding 0.0004 to 2,000 is really not changing the number much, right? So that even if we can measure this a little bit really, really accurately, we did not measure that 2,000 really, really accurately. Unless, of course, it's 2,000.0000. That tells you we measured that 2,000 really accurately, right? So, significant figures, they're a sticky widget. You're, look it up. But mainly, it's just count the significant figures. When you're multiplying, your answer should be rounded to whatever the lowest one was, right? So if you had 2 sig figs, 3 sig figs, 4 sig figs, if you're multiplying, you round to the one with the lowest number of significant figures. If you're adding, then what matters is decimal places. So decimal places for addition and subtraction. It's whatever your smallest decimal is. And if one of those values has no decimals at all, if there's no 0.0, then your answer should not have decimals. But in every case, you're going to round to match the number of significant figures. So if it's 0.4, it becomes whatever that was. If it's 0.5 or up, it becomes one more than that, right? So that's where that 158.7 comes in. If it's round to 3 sig figs, what would it be if it was round to 2 sig figs? What would that answer be if it was 2 sig figs instead of 3? 160. Because then we'd be looking at 15 as the 2, and what's the third one that we don't want? 8, that rounds, so it's 16 or 160, right? I did have one person that answered some of their homework questions in scientific notation, and I was like, that's creative, but you had to know there's no way I was going to anticipate that one. So everybody got a lot of them wrong just because I was trying to guess. But there's there's a finite but large number of ways that you can answer these questions. So really the take-home lesson for me is don't do fill-in-the-blank questions, which I kind of already knew that. I was just trying to see how well it would work. So I might just have to invent some multiple choice or true false or turn the questions into something a bit more like that for future homework. And then this one, that last question on there where it talks about melting ice, right? It's a beautiful thing and I really liked it, but here's the way it works. You had a known, all right, before we even get there, let's talk about this. The reason why I drew this up here, these are equations that you guys don't recognize. I just made these up. The point of writing these two things is, because they are both equal to E, if we are talking about the same system, that means that I can put this equal to that. Because if 2 horses are equal to 1 goat, and 1 goat is equal to 2 chickens, that means that 2 horses are equal to 2 chickens. Did you follow that, or did I just confuse you? So, if we're putting this here, what I can do is I can take that E and draw out that same equation right here, and that is still true, right? Because this right here is true, that's what it was originally, and this right here is true, which means that whole thing is true, which means I can get rid of this thing in the middle and just do that, and then solve for, say, the change in time for whatever the heck those other variables are, if you have them all. Which in that problem, in that homework, you did. You had everything except for the amount of water that was in that container. So you could have done this if you really liked algebra. Or you could have done it without it, by simply conceptualizing the answer, breaking it into two parts. Because the important thing that was there, the part that may have been confusing, is it was asking you two questions. How much energy does it take to melt a known volume of ice? Right? And it was also asking another question, how much volume by weight, how much weight of water can you cool 8 degrees with this much energy? Those were the questions. The first one told you how much energy you had to work with. The melting of that ice, that told you how much energy you had to work with. That was the number you plugged in to the second equation to find out how much water that was enough energy to change by 8 degrees. And then, of course, you do the standard math of rounding to significant digits because there's a lot of multiplication and division there, right? So, I like that question, especially as a homework question, because it does force you, if you're going to figure it out, it forces you to go, I know this thing, and I know this thing. Can I take these two balls and actually see that they will stick to each other, that they are related to each other? Because otherwise, you know a bunch of things, and it's just a whole bunch of balls that have no connection to anything else, and that can get really daunting. Having to remember just a whole bunch of random, disorganized, chaotic, and unrelated facts, that's crazy. But if you can organize those facts in your head, so that it's not 1,000 unorganized, unrelated facts, it's actually groups of facts that are related to each other, based on certain themes, then that makes individual little pockets of that a lot easier to grasp, and a lot easier to remember, and a lot easier to apply. Because otherwise chemistry is just a huge list of a lot of facts that don't have anything to do with each other, because you don't understand that they have everything to do with each other. So, that's that. I'm going to dive into chapter 6, because we really need to get that started. But, especially if we are actually kind of sort of keeping up with where we need to be, we can spend some more time talking about either the homework or the test. And then once class is over, I'll give you some pointers and remind you about some things about the test. Right? If we don't finish chapter 6, and by finish I mean, reasonably get to the end. If there's like 2 slides left, then I might just kind of be like, finish those 2 slides. And then it'll be on the test that opens tomorrow. If there's still 30 slides left of this chapter by the time we quit for tonight, then it won't be on the test. Now that doesn't mean that you won't have to worry about it. It just means that the test will be 48 questions over 3 chapters instead of 48 questions over 4 chapters. Which might be easier because there will be no questions about chapter 6. But it also means there's going to be a lot more questions about chapters 2, 3, and 4. And 2 and 3 were 80% math. So now if that's math that you feel very confident you can do, then that might be in your interest. But what that does mean is that chapter 6 is guaranteed to be on the next test. So the next test might have 5 chapters on it, which means there'll be 50 questions, 10 from each chapter. Right? So you're not getting out of it. It's not like there's not enough time to clean your room, so you don't have to clean your room. We're just going to do it next time. Right? So, let's talk about chapter 6. What are we trying to do? Chapter 6, ionic and molecular compounds. Let me go kill the light so we can actually see the screen, shall we? Fix that top. Thank you. So, here's a nifty thing that you may or may not know about most of the medications that you might give to someone. Most of the medications that you're going to be injecting, if it's in pill form, this will not be the case, but if it's in injectable form, well, actually even in pill form it might be. But certainly if it's in injectable form, it's going to be an ionic or like a salt, a version of an ionic compound that we use in order to create those medications. So, now it's probably not going to be part of the name, but as an understanding of chemistry, I would hope that you would be able to understand why it is these ionic compounds that we use in order to dissolve and store some of these drugs that we use. All right. So, ions. Transfer of electrons. The goal here for 6.1, and I should point out there's, I think, 9 sections of this chapter, which is why I'm going to try and move quickly. It's why we have, there's like 100 and, actually it's not showing it there anymore, 100 and some odd, 117 slides. It's a lot. So, an ion is where we are not sharing electrons. See, and this is a critically important thing. The whole chapter is not about ions per se, but the first section here is about ions. There are 2 ways to have, that's not true, there's more than 2. There are 2 primary ways to have really strong molecular interactions within the same molecule. One of them is covalent bonds, which we'll get to in a little bit, and the other one is ionic bonds. Both of them have everything to do with where the electrons are. Covalent bonds, you are sharing electrons, like 2 kids at kindergarten in the playground that have learned how to share, and they're sharing their toys with both of them playing with them. An ionic bond is more like one kid that's a little bit of a bully who steals the toy, and then the other kid is just kind of hanging around because he really, really wants it back. He's attracted to that toy, if you follow the metaphor. So in the case of ionic interactions, we are transferring electrons, but one of the atoms is going to be the one that owns that electron. It will be holding on to that electron solely, which will give it a negative charge. And the other guy, having lost an electron, or more than one in some cases, but in the case of sodium chloride here, the sodium loses 1 electron. Why? Because it's over in that first group, right? And so it has only 1 valence electron to lose before it's nice and stable. So it will lose an electron. Chlorine is over in our halogens, so it's going to gain 1 electron to be nice and stable. But when you have, in the case of sodium, 11 positive charges, and when we lose an electron, that gives us only 10 negative charges. So what is the charge of sodium? Positive 11 minus 10 gives you a sum of positive 1, right? So that's where our positive comes from. Chlorine has 17 protons with 17 electrons, but if it takes 1 from sodium, it now has 18. So 17 minus 18 gives you a charge of negative 1. And so that's where we have our positive and negative charges. And what happens to positive and negative charges if they are associated with each other? They do what? They are attracted to each other, right? Just like a magnet. Question?
So you're saying one atom will hold on to the electron of that specific element, and the other, I guess, atoms of a differing element will hold on? I mean, we'll try to take that electron.
We'll give up the electron.
We'll give up the electron.
One of them is donating its electron to the other one. And I don't want you to think that it's just like, here, you can hold this for me while we're hanging out. No. Chlorine is taking it.
And it's always a different element?
Yes.
Okay.
Well, yes.
Okay.
For our purposes in this class, yes. Especially for this chapter.
The one that takes is always the negative.
Correct. Well, assuming we're starting with neutral things to begin with. In the case of chlorine, yes, if we start with a naked sodium, a balanced sodium atom with 11 protons, 11 electrons, and we have a naked chlorine with 17 protons and 17 electrons, then yes, if that chlorine takes 1, it becomes negative. Now, the reason why I'm prefacing this is because later on when we talk about chemistry, biochemistry, and otherwise organic chemistry, we're going to have molecules that are starting out with a +2 charge. They're going to take an electron and then leave them with a +1 charge. So it's still positive, but it's not as positive as it used to be. So I don't want to say the one that takes an electron always become negative. But yes, if they start at neutral, yeah, you start at 0 and add a negative number, you're going to be negative. Right? So, now, could we have something that takes more than 1? Change this salt to something that I would not advise you ever actually ingest. To something where that second guy is taking more than 1 electron. Not so much from sodium, but just wants more than 1 electron. What could you do?
Hydrogen.
Hydrogen wants to give up, not gain. So we have, actually hydrogen wouldn't mind gaining, but then, other things happen. So if we take our chlorine over here, if we just move over to sulfur, sulfur wants to gain not 1 electron in order to be full, but 2, right? So we could have an S2 minus, but then we would need how many sodium ions in order to balance it out? we'd need 2 sodium ions. So the salt for sodium sulfide would be disodium sulfide. It would be 2, actually that's not right either because we're going to nomenclature later, but it'll be 2 sodium ions and 1 sulfur ion. But the sodiums will both be +1, and the sulfur would be -2. So, ionic compounds are compounds that are held together because of ionic interactions, which means that they only happen when you're drawing these things out if you're doing it completely and there are pluses and minuses involved. If there's no pluses and minuses involved, then it's not an ionic compound. Ionic compounds are things that stick together specifically and only because of the attraction between positive and negative charges. If you are holding on to electrons that you are actually sharing, and I'm going to use the word sharing in air quotes here between hydrogen and oxygen in water because oxygen never shares well, but it's still technically sharing its electrons with hydrogen, and so that is a covalent bond. That's not an ionic bond where one takes it and then they're attracted to each other because of the positive negative. It's because they're sharing it between them and they are now covalently bonded together. Both of these, ionic and covalent bonds, form relatively strong interactions between atoms. Covalent more so than ionic. So, what are the bonds that are holding this C3H8 molecule together? Are those covalent or ionic interactions? Do you see any positives or negatives anywhere on this label? No. So if it's not holding together because of positive-negative association, then that makes it covalent. Now, I do want you to be careful. This is a good way of understanding the difference between ionic and covalent, but that being said, how many times have you seen sodium chloride drawn with positives and minuses in it? Not very often. So an ionic compound frequently will not have that positive or minus drawn in it, especially when you're talking about other places in the book. But when we're talking about different types of bonds, we draw them there so that you can appreciate this is an ionic interaction, as opposed to a covalent. Now we will talk about some rules about which things tend to be ionic bonds, which things tend to be covalent bonds. I just don't want you to get confused if you look at sodium chloride on a salt shaker and go, they're writing this wrong, because there's no pluses and minuses here, right? All right. Chemical bonds, covalent bonds, and ionic bonds are formed when atoms lose, gains, or share. I want you to do yourself a favor and put quotes around valence electrons. Mostly what we're going to be talking about, it is true that we are forming covalent bonds because we are gaining, losing, or sharing valence electrons. But if you go beyond the boundaries of what we're going to spend a lot of time talking about, and we'll spend a little bit of time in Chapter 6, but beyond the boundaries of this class, it is not always sharing valence electrons. Or you could say, well, that's not technically true because under certain conditions it forces a subshell electron to become a valence electron, and that's splitting hairs. But for our considerations, for everything that we're going to be working with in here, it's a valence electron that is being shared. And the whole point is to get to an octet. The whole point is to get to 8 in your outer shell. Unless, of course, you're talking about hydrogen or helium, in which case their outer shell only holds 2, right? Because that first shelf in our metaphor of shelves from Chapter 4 only held 2 books, right? If we're following that metaphor, how would you rephrase this sentence in order to make it fit that metaphor? We're trying to gain or share valence electrons to acquire what? A full top shelf, right? To make sure that that top shelf has 8 books or 8 electrons. Now that either means filling up a shelf that's almost full or emptying a shelf that's almost empty, right? The point is we want the highest occupied shelf to be full. Ionic bonds occur, as I said before, usually between atoms of a metal and non-metal. There's your first clue if you're looking at an ionic compound versus a covalent compound. Are you looking at a metal and non-metal together? Well then, that's probably ionic, because metals like to lose electrons, and ionic compounds like to gain electrons, or excuse me, non-metals like to gain electrons, and so there's your first clue that this might be ionic. If you're looking at a lot of intermediate, or a lot of, say, carbon, nitrogen, hydrogen type stuff, then you're probably talking about covalent. If you're talking about non-metals with non-metals, those are probably covalent bonds. So here we have the example. Here we have a metal and a non-metal. The metal, abbreviated M, that's not actually supposed to be a chemical symbol. We're not talking about mercurium or something. There isn't actually an M by itself on the periodic table, just like there's an NM. But metal, M stands for metal, NM stands for non-metal here, right? So our metal with one electron, it's going to give or have stolen, depending upon how you look at it, its electron to the non-metal, which is going to fill up the non-metal's shell, right? And it will also leave the metal shell, that top one now empty, which means the one below it is full. How do I know the one below it is full? Because when we were talking about filling up the shelves, did we ever add an electron to a shelf up before we filled the shelf we were on? No. At least not as far as we got, not as deep as we got. You always fill up the shelf you're on before you move to the next one. Now, that is not true if you keep going deeper into the periodic table, but for our purposes, it is. So, here we have, thank you, here we have the ionic association. That metal lost an ion, an electron, so it becomes positively charged. The non-metal gained an electron, so it becomes negatively charged. And now these two guys stick together not because they are sharing electrons, but because they are positively and negatively charged, and those two different attractions, those two different charges attract each other, right? What's the difference here between our two nonmetals? Both of these nonmetals have 7 valence electrons. How do I know? I counted the dots, right? So, what's it going to take to fill up their outer shell? Each one of them needs one more, right? Now, if there was a metal around, they could just steal one and be good, and become an ion. But what they could also do is play nice with someone else that also would like to share an electron. And so one of them says, I'll share my electron with you if you share your electron with me. And if they both of them share, then that means both of them get to have a completely full octet, right? If you count how many dots are around each one of them as a center, how many do you see? 8 for each. 2 of them are shared, but there's still 8 for each, right? Positive ions form when things lose electrons. So, your metals, especially in group 1, 2, and 3A. So that's your lithiums, your sodiums, your magnesiums, your calciums, your aluminums from 3A. The metals tend to readily lose 1 or more. Why or more? What would the ionic charge of magnesium be? Magnesium is in group 2. So how many electrons does it have to lose before its outer shell is empty / lower next shell down is full? 2. So that means that it will readily lose both of those electrons in order to form ions with a positive charge. They will keep losing electrons until they have the same number of valence electrons as the nearest noble gas. In other words, they're going to drop down. Magnesium will lose 2 to be the same as neon. It's going to try and lose those extra books off that top shelf, so the one beneath it is full. Right? Metals will lose electrons. By the way, anybody remember the name that we would give, not that we're going to spend time doing that math here, but the name that we would give to the amount of energy that it takes to rip off that first electron? We talked about 2 days ago, guys. What are we making when we remove electrons? We're making ions So it's the energy of ionization. Does that ring a bell? Maybe? It's different for different atoms, right? And that's going to be based on how far away. Remember when we talked about those trends on the periodic table? What happens to the energy of ionization as we go down from lithium to sodium to potassium to rubidium? What happens to the energy of ionization? It goes down. It gets easier to remove electrons because the electron is further away from that positive charge, right? What happens to the energy of ionization as we go right through the group? We're getting more and more positive charges in the same distance, so that the size gets tighter, which means they're closer, which means the energy of ionization is going to go up, right? So, a little review from last chapter that we talked about, right? So here we have our sodium atom that is losing an electron. What happened to the size of that sodium atom that is represented here in this picture by the amount of blue cloudy space around it? Why did it get smaller?
Lost a shell.
Because it lost one atom and that outer shell is now empty, so we don't count it, right? Which means the size of the atom, the distance between the nucleus and the furthest out electron is now much smaller. Because the furthest out electron is on that lower shell. So we can literally change the size of atoms, not the size of the nucleus, but the overall size of the atom can change via ionization. Because we're adding or subtracting shells, right? In the same way that as we go down the periodic table, down the group, right, the size of the atom gets bigger, right? Because we're adding more and more shells. Each time you go down one more period, it gets one bigger. Go down one more period, it gets one shelf bigger, right? Those nesting dolls, they keep getting bigger and bigger and bigger as you put it inside the next layer, right? Magnesium, as an example that we've already talked about, is a group 2 when it's neutral, so it has 12 protons and 12 electrons. Magnesium wants to lose both of those outer electrons, those 2 electrons in that top shelf, because then that makes it have only 10, but 10 is the 8 from the second shelf and 2 from the first shelf, right? Which means all of its shelves are full, it's nice and happy, but it's also a negatively charged ion now. Excuse me, positively charged ion, because it has 12 positives and 10 negatives. What's that add up to? Positive 2, right? Once again, they want to get down to where their highest bookshelf is full, where their top outer layer of valence electrons has 8. Those are 2 different ways of saying exactly the same thing. Non-metals, on the other hand, out in groups 5, 6, and 7, why not group 8? Why is group 8 not in this list? And you could say, well, it's because they're not non-metals. Okay, we have a different name for the things in group 8.
They're noble.
They're noble gases. So why are they not listed here as things that like to gain electrons? Because they're already full. Their top shelf is already full, right? They don't need to gain anything. So out here it says that these guys have very high in 5, 6, and 7. So nitrogen, oxygen, and fluorine on that top row that we frequently talk about, right? 5, 6, and 7. Those guys like to gain electrons. Not just one. Well, fluorine and chlorine and bromine and iodine, those guys only need 1, right? But oxygen needs 2, right? And nitrogen, how many does it need? It's in group 5. How far away is that from 8?
3.
3. So it wants to gain 3, right? But it says that these guys have really high ionization energies. I don't want you to get confused by that bullet point. So what does that mean? Tell me what that means. Inversely, it means that our metals have really low ionization energies, right? Why would that be? Because metals want to get rid of that electron, right? Why would it be hard to remove an electron from oxygen?
Because the valence electrons are closer to the nucleus.
The valence electrons are closer to the nucleus because they're all the way on the right. Remember what we talked about? As you move down the periods from the left to the right, what happens to the energy of ionization? It goes up, right? So the energy of ionization is going to be higher because they're on the right side of the periodic table. That is an accurate answer, but now put it in terms of something that's conceptual that makes some sense. That's not just pure chemistry talk. Why would it be hard to remove an electron from fluorine? It's only one away from being full. Why would it want to give up an electron and be even further away from being full? Would giving up one electron make it empty? No. It would have to give up not just one, not just two, not just three, it would have to give up all of them, right? So ripping that first electron off is hard because it's really close to the end, or, more appropriately, because it's on the far right of the period, and therefore the electrons are more closely associated with the nucleus, which makes the ionization energy higher. Whichever of those things makes more sense to you. They're going to gain electrons until their valence shell is full, until their top shelf is full, right? What's going to happen when they gain those electrons? So here we have a chlorine atom. We gain one valence electron. I don't actually like the way this is being drawn because it's not really doing this. So we have 7 electrons in our shell. We gain one more electron and it makes our shell look like it just had the same increase in size. But is it really getting that much bigger? Are we adding another shelf to this? Are we adding another nesting doll? No, we're just filling up the shelf that we already had stuff on, right? We're not going to calculate sized atoms, so it doesn't matter that the art here is not exceptionally realistic. But I did want to point out that minor error in presentation. So that naked chlorine becomes chlorine minus 1, right? Because it gained 1 electron. All right, so the names of common ions. We have cations. Cations are the ones that are positive. Anions are the ones that are negative. I don't really have a good metaphor for this. Like, well, cats are always positive, so that's why cations are positive. Anybody who has a cat knows that that's not true. Cats are usually pretty pissy. So why don't we call cations the negative ones? I don't know. Like, anions kind of sounds like anabolic, and anabolic steroids are bad, and that's just too much of a stretch to make it easy to remember, right? So I don't have a good metaphor for this, so cations are positive and anions are negative. I can't help you out with that any further than that. You'll just have to remember that. So what do we have? Lithium, sodium, potassium, nitride, phosphide, oxide, sulfide, fluoride, chloride, bromide, iodide. Why isn't it just iodine? Are we changing the names over here much? Lithium, what do we call lithium when it's not positively charged? Lithium. What do we call oxides when it's not negatively charged? Oxygen. There's a reason that these have this name, because if I have a potassium positively charged thing with a fluoride negatively charged thing, what's the name of that salt? Potassium fluoride. IBE tells you that it's an ionic compound, and it also tells you which thing is negative and which thing is positive. The ides, are negative. We use the group numbers 1A, 2A, or 3A to determine the charge of these ions. Now, could a magnesium atom lose just 1 electron and have a +1 charge? Could it do that? Conceptually, is that something that could happen? Yes. Does that happen in ionic chemistry? No. Especially not at the level that we're discussing in this class. So, what that means is the ions in group 1 will always have a +1 charge. It means the ions in group 2, if it is an ion, it will have a +2 charge. And if you are in group 3, all the way out on the end over here, why is it only listing aluminum? Why isn't it listing gallium or the things below gallium? Well, that's because aluminum is a metal that acts like a straight metal. There are other metals that are very common metals like iron and copper and things like that, manganese, that are not on this list anywhere. Why not? Well, we'll see them in a minute because they're weird. But everybody that we care about in group 1 is on this table. Everybody we care about in group 2 is on this table. That makes them easy. That makes them straightforward. Nitrogen, oxygen, phosphorus, potassium, sulfur, chlorine, selenium, bromium, and iodine. Arsenic is not on this list. I don't know what Te is off the top of my head. Can you tell that I also did not go through chemistry with teachers that required me to memorize the periodic table? And if I did, it was so long ago, I would have intentionally forgotten.
What about beryllium? Or the B?
Boron?
No, the BE.
In what group?
Two.
Oh, all the way at the top, you're right, it's not there. Okay, I stand corrected. We'll see if it actually shows up on the second table. Because I don't, yeah, that one might be a poly as well. These guys here are singles. They only show up in one ionic form. Which begs the question, what about the other ones? What does that imply the other ones can do? Multiple forms. Alright, so here's some important ions that are especially significant for biology. Sodium, potassium, calcium, and magnesium. Sodium is the principal cation outside of the cell. Potassium is the principal cation inside the cell. You spend, I'm going to go out on a limb here and say, if not the majority, you spend a massive amount of energy, of the ATP that your cells get from your food, from burning your food, a massive amount of that energy is spent on pumping sodium out of the cell and pumping potassium into the cell. So much so that there are millimolar concentration differences between either side of the membrane. Why would you do this? We've talked about it before when we were looking at a picture of a dam. What can you do when there's a really big height difference between the top of a dam and the bottom of a dam?
Potential energy.
You get a lot of potential energy out of that, right? If you harness it right. Well, that's what your cell is doing when it's pumping those sodium and potassium ions. It is using your cell membrane like the wall of a dam and creating a huge difference between the outside and the inside. So that if it opens up a little bit of a spill gate, it can harness all of the energy. But you say, that's nothing like a dam, how does that work? Yes, you're right, but the potential energy of a chemical gradient is just as real as the potential energy of a ball falling or as water falling from the top of a dam to a bottom. It's a real thing. We're not going to do that calculation yet, if at all, but it's a real thing. It's just as real as gravity.
One of the techniques vets use not to get kicked by a horse is they'll hit the skin so they completely deplete any potential energy in the nerve cells, and then give the injection because there's a recharge time.
Right.
If they can get it in there quick.
So effectively, if you make all of the pain receptors fire fast enough, you have a very short amount of time where the next poke is not going to register as a real bad poke. I can believe that because you're right. There is a recovery period of neurons. Because remember, I mentioned earlier, a neuron only has two ways of being, right? It's either not saying something or it's saying, hey. It takes a little while to reset that hey button. Regulation and control of body fluids. We get it from salts, cheese, bananas, potatoes, orange juice, all sorts of fun stuff. Can you die from drinking too much water?
Yes.
Yes.
Yes. Why? Has nothing to do with drowning. It's not because water starts to leak in your lungs, there's no other place to go.
Because osmosis causes an imbalance. Everything.
Yes, specifically, The thing that kills you is the imbalance of this. If you dilute the fluid outside of your cells too much, then those batteries that your cells have spent all of that energy trying to maintain, if they can't actually tap that, if they can't plug into that energy anymore, it causes everything to go foobar at a cellular level. Just from drinking too much water. Too fast. You can drink enough water to kill you, but if you spread it out over a long enough period of time so that your kidneys and your sweat glands can get rid of it, then you'll be fine. Because over the course of a year, you drink more than enough water to kill you. The difference is, you drank it over a year. It's a colloquial story, but there's like, the one that I like to use is, I remember hearing a radio story, maybe a little less than a decade ago, a radio station that ran a competition of how much can you drink, don't pee for a wee. They were like, the one who drank the most was going to win a wee gaming system, and the winner was awarded the prize posthumously because she died. But at least her family got to enjoy a wee. Sure, it was totally worth it. Calcium, cation that you find outside the cell and in the bones, we use this for muscle contractions. Calcium flooding into your muscle cells in response to a nerve impulse is the thing that makes your muscles contract. Because it's the thing that activates the fibers, the tiny little proteins in your muscle cells. They are always wanting to pull. Because that's what muscles do. They always pull, never push. They are always wanting to pull, but the problem is most of the time they can't because they don't have any calcium. And if you don't have calcium, then they can't bridge the connection between the two different fibers that want to pull. Question?
So how are extensor muscles working?
You have muscles that can help extend something, but that's still pulling on the backside of a joint, if that's what you're talking about physiologically. Muscles never push. They always pull. That's the way muscles work. At least to my understanding of physiology. You can find something that I'm completely unaware of.
No, it's making sense now.
Right, just like every set of muscles that you have of skeletal muscle always comes in a pair. Your bicep that pulls your arm closed. How do you get that arm straight again? The tricep pulls on the opposite side of the bone. Muscles always pull. So even the thing of act of straightening your arm is still a muscle that's pulling on the back of that bone. All of that requires calcium. Not enough calcium, muscles don't work well. Magnesium, another cation found outside the cell, also is involved in muscle contraction and frequently involved in cramps. When you have poor magnesium distribution. Alright, so let's talk about some ionic compounds. They're going to go here. We need to be able to write the charge balance, which we should already be able to do because we've talked about that, right? And write the correct formula for an ionic compound. What's the formula for sodium and chloride? Well, they're both +1 charges, right? So the formula is sodium chloride. +1, -1. The whole point is, when we add that +1 and that -1 together, what do you get?
Happiness.
Happiness of 0. Ionic atoms will form ionic compounds that are no longer ionic. An ionic compound should have a charge of 0.
Would it be wrong, metaphorically, to think of it as symbiotic?
As a metaphor, that might sort of work. I mean, I don't know what benefit they're getting out of it because they're not happier when they're around other charges. They're certainly happier than they would be if they weren't around other negatives. So the other charges protect them from the negative charges, or vice versa, sure. Now, I should point out the thing that I just told you. Ionic compounds are always going to be 0. You can put air quotes around that if you'd like, because we're going to talk about ions that are made up of multiple atoms that still have a charge. You guys heard of sulfate, phosphate? Heard of these things? Nitrates? These are multiple atoms put together that still have a charge, but we very rarely find them floating around in their ionic form because they're used in making ionic compounds where the total compound has 0. positive, negative ions, they are attracted because of the ionic bonding between those two things. They tend to have high melting points. Why? Because ionic bonds are strong. What's melting mean? It means going from a solid to a liquid, right? In order for something to be a liquid, individual atoms have to be able to move around each other constantly and fluidly. And ionic things don't like doing that because, well, there's those positive charges over there, negative charges over there. We don't like to hang out with one of those. We really like to hang out with the other one. So there's high melting points because it takes a lot of energy to loosen those bonds enough that they'll start sliding around. So if they have high melting points, room temperature is not considered a high temperature, right? So if your melting point is very high, what state will you be in at room temperature? Solid. Sodium chloride, table salt. If you magnify crystals, it'll actually be able to show you that there is a crystalline organization, there's a lattice structure. If you get down close enough, you can actually see that as it's drawn here, with our sodium and chlorine ions, intercharge or arranged, what do you notice about that? If we could zoom in on it a little bit more, you would see that every sodium, those tiny little purple dots, they are surrounded by negatively charged chlorine atoms. Why wouldn't they have other sodium atoms anywhere near them? Because positive charge repels positive charge, right? Because just like before, as each one of those sodium is surrounded by chlorine, each one of those chlorines is what? Surrounded by sodium. When we talk about covalent atoms later, you're going to have an individual chemical formula, and there will always be an exact ratio for that chemical formula. What's the ratio of sodium to chlorine here? It's pretty much 1 for 1, but it's not divisible. We can't pull one of those things out. Because that one sodium doesn't belong to the chlorine next to it, it belongs to all of the chlorines around it. They're all holding on because they all like that ionic interaction just as much as everybody else. So, when we write the chemical formula for these guys, we write them in terms of the lowest whole number ratio of atoms or ions that we can in order to make the charge equal to 0. Because complete ionic compounds are going to have a charge of 0. Once again, with that little asterisk next to it, that there's some other guys that make this messy. And we'll talk about them in a minute. So sodium chloride becomes sodium positive charge 1, chloride becomes negative charge 1. So we write this as sodium chloride because we don't need just a 1-to-1 ratio is good, right? Sodium, same name as before, right? But chlorine is not chlorine anymore, it's chloride, which tells you that this is an ionic compound. So manganese chloride, or magnesium chloride, excuse me. Magnesium has 2 electrons that it likes to lose, so it will give 1 to each of the 2 chlorines, because chlorine will only take 1. Why would it not want to take 2? If it likes 1 electron, why wouldn't it like 2 electrons? Right, because only 1 gives it a full shelf. If it takes 1 more, what's it doing? We're adding 1 more to another shelf now. That defeats the purpose, right? So in order for that magnesium to lose both of its electrons, it has to find 2 chlorine atoms to give it to. So we have a +2 for the magnesium. Chlorine's only -1, so how many chlorines do we need? We need 2 of them. So what's the whole number, smallest whole number ratio of these 2 atoms? Magnesium 2 chloride, or MgCl2, right? You wouldn't put magnesium 2 chloride like this. Why? Because people might get confused and think that that 2 is right here, right? Which we're going to talk about that for test prep later, just in case we have to. But that's only if we get through all the way through this chapter. Because this chapter is a pain in my butt when it comes to putting these questions online. Because transferring these questions into D2L does not allow for fonts, which means subscripts and superscripts don't transfer. Which means I have to type all these things in manually in D2L, and that's a pain in my butt. But, you know, I'm a dedicated teacher and stuff, so do it.
They won't let you use an illustration?
If I want to upload them all and link to them, which would take even longer than just adding it manually and tell. Because in D2L, I can tell it's a superscript subscript. But after I write it in, so like every individual 2 and 3 and whatever has to be superscripted and subscripted in every question. I hate it. But this is a chemistry course, so this is like, oh, this is going to suck.
Can't you copy and paste them from another program?
You-
Set it up in Word or whatever?
See, you'd think so, yeah, but not for D2L.
Really?
For D2L, it can only import it as a comma-separated limited file, which means it has to be straight text, which means you can't use superscript subscript. If I could get it imported into Blackboard, which could do a better job of it, and then that exported as a unit, which could then be imported into, but I can't do that because we don't have the thing that makes the Blackboard thing that makes the. These are my crosses to bear, not your crosses. So,
Can your CBL file include markup?
CSV, comma separated file. So no, it can't. It's just straight ASCII text.
Well, I mean, markup is ASCII text.
You mean the HTML markup? What are you talking about? No, I tried it.
Okay.
And plus, typing it all into HTML doesn't really save me time either.
Well, you can paste formatted text into something like Word. And
Oh, and
export
then have it
that.
displayed as HTML. That's true. But no, I tried it. It doesn't work. Not in the import.
Got to just.
So, here we have sodium and a sulfur atom. So sulfur wants how many electrons? It's in period 6. That is how many shy of 8?
2.
Should say group 6, not period 6. 2. So it needs to get 2 electrons. Sodium can only give 1 each. Why can't it give 2? Well, technically it could, but it's only got 1 in its valence electron, right? And so if it gave 1 more away, then that top shelf wouldn't be full anymore, and that defeats the purpose. So it'll only give 1 away. So now we have sodium has 1 positive charge, sulfur has 2. So how many sodium atoms do we need? 2 of them, right? So this is Na2S. Sodium sulfide. Question?
Oh, when is it sulfate?
We will get to that. Sulfate, sulfite, hyperchlorite, hypersulfite. Yeah. Fun stuff! And those are the things where ionic compounds that don't have a 0 charge, but that's why they are a compound that is part of a compound. Right? So we'll get to them, I hope, eventually. So how do we name this? Morton salt. That's not how you name it, that's just a brand. What's that?
Nothing.
Okay. So when we name an ionic compound, we write the metal first, and it's just the same name as an element. We've already seen this, right? We talked about it before. Sodium is not sodium chlorine, it's sodium chloride, right? But we use the metal name is the same, and then the non-metal gets the same first syllable, chloride, fluoride, bromide, iodide. We use the first syllable of the non-metal and then add the "ide." That tells you it's an ionic compound. This is how we name things. This is also why you'll note that we have not had any dis or tris or tetras, right? What do we call this guy all the way back here? There's 2 sodiums and 1 sulfur. Why isn't this disodium sulfide? Well, because if it's an ionic compound, we don't need that. It's just sodium sulfide. Because sodium has a charge of +1, sulfide has a charge of -2, so that tells you how much of each one you need, right? Question?
Just like, is I always going to be an ionic ending in this type, or no?
I'm going to say yes.
Okay.
Trying to think of other. Yeah. I'm going to say yes. until we see something that says otherwise. Put a space between the names of the metal and the non-metal. Potassium iodide, magnesium bromide, aluminum oxide. It doesn't matter what the numbers are here because it's an ionic compound. And so we don't need tetras or dyes or any of that. It's just the metal and the non-metal. Because potassium iodide is easy, right? +1, -1. So that just means it's a 1-to-1 ratio. But what's aluminum oxide? Aluminum's +3, oxygen or oxide's -2. So what's that going to be? What's the smallest whole number ratio that you can get to make the total pluses and minuses equal 0? 6. So that means we need how many aluminums? 2 of them. And how many oxides? 3 of them. So Al2O3, but we just call it what? Aluminum oxide, because it's an ionic compound. Everybody follow? Name this ionic compound. Potassium oxide. The metal is the same. Oxygen minus Gen plus I. Oxide, right? Potassium oxide. How much would it take to do both? Well, oxide is a -2 charge, so we need 2 potassiums, right? So that's where that K2O comes from right there, but we still just call it potassium oxide. Everybody follow? We're good on that one? Here's some example for naming. What would that be? Calcium oxide, that's what? Aluminum sulfide, that's magnesium chloride. Beautiful. Walking all the way through that. I should have removed these. Why did I not remove these? Did I just miss them? All of this should be in the problem set. I guess I just missed them. Alright, here's the thing. So far, this has been easy. This has been simple. Remember that table where I told you these guys are simple? They only come in one form, right? Beautiful! Alright, now we get the troublemakers. So here are some other metals. Copper, but we get copper 1 or copper 2. Iron, we get iron 2 or iron 3. You can get more than that, but we're not going to talk about it. You can get lead 2 or lead 4. You can get chromium 2 or chromium 3. There is a finite amount of ways in which these things will be comfortable. In the same way that, yes, you can get a magnesium atom and you can force it to lose only 1 electron, but it's not going to stay that way, because that's not stable. But this is iron. Where's iron on our periodic table here? Fe, blip, right there in the middle of our transitional elements. Cobalt, blip, right there. Nickel, right there. Copper, right there. Oh, where's chromium? Chromium back there behind manganese. Our transitional elements. Now remember, what was weird about our transitional elements when we were talking about those shelves? When it was that first shelf only has 2, and the next shelf has 8, and the next shelf has 8, right? What was weird about those transitional elements? We like to say that that 4th shelf only has 8, right? But actually, it has another 10. So that 4th shelf can actually hold 18. And that's why these transitional metals here in the middle, these guys are the troublemakers. Because sometimes a non-valence, something that you would consider to be a non-valence electron, reacts as if it's a valence electron. So that's why iron can lose 2, or it can also lose 3. Now, would we name things the same? Our naming nomenclature is going to be the same thing. So how can you tell the difference between a copper ionic compound that is copper 1 versus copper 2, right? Because if this is, let's say, copper oxide, does that tell you what you have? No, because do we have 2 coppers for every oxygen, or do we just have 1 copper for every oxygen? So what would we need to add to this name so that we can be clear when we're naming our copper oxide, which one it is.
Have a different ending.
We could have a different ending, sure, or we could just do exactly what they're showing us here. We could just name the copper. Here's some bismuth. Yep, so that answers your question. Bismuth. Bi? No, your question was about
It's beryllium, isn't
Be.
it?
Yeah, I think it is. I don't know.
'Cause
I
I
have to
know
look it up.
Br is boron.
Right.
You were talking about E, right?
Or,
Isn't it?
yeah,
It's
B.
beryllium.
Beryllium.
Yeah,
I don't see it on here.
because I didn't.
I don't know why it wouldn't make ionic compounds.
Can you
So-
do it with beryllium though?
Can you what?
Like, if it was a question, can you do it with beryllium?
I don't see why not. I mean, there might be something special about it that makes it so uncommon as to be not worth talking about in an introductory textbook. But conceptually, yeah, it can make an ionic compound with whatever it is that fills it up. If it only makes one ion, or if it makes two.
How do you know if it's 3 or 4 or 2 or 3? Again?
Well, depending on what you're looking at, by the name, or by the formula. So, if, like, for example, I could say, in this salt, where it's Fe2PO43, which is iron phosphate, what's the iron? Is this iron 2 or iron 3? Well, to figure that out, you'd have to do the math. How much negative charge do we have here? So how many positive charges do I need on the iron to equal it out, right? Or I just call it iron 3 phosphate. So, there you go. So, when we're making our salts, when we're naming them, these troublemakers, all of these guys right here, this table right here, you can't just call it copper oxide. You can't just call it copper formula I, right? Whatever the other thing is. It's got to be copper 1 or copper 2. The name is not complete unless you tell us which one it is. And the reason for that is because all of these guys can form either of those ionic states relatively easily. So we have to know. It's not like one of these things only occurs once in every 10 million molecules. So this is a nice table. When we get to things like tests, where you might need to look something up that's useful for certain portions of chapters of questions, being able to know where things like this, where we have a high amount of information in a concentrated area, might save you some time. Just saying. We've had a few other tables that are like that too, right? Tables with a collection of conversions that might save you some time if you could quickly find that table. Because I don't expect you to memorize all of this stuff, but I do expect you to be able to find it and answer questions about it. Okay? Make sure. Mercury 1 ions form an ion pair with a +2 charge. Okay, sure. Mercury 1, but it's listed as Hg2 2+. So you're only going to find Mercury 1 ions if there's 2 of them together. So in other words, you're never going to find Mercury 1 chloride. Because Mercury 1 is not stable unless it comes in pairs. So you could have Mercury 1 oxide, but that would be Hg2O, right? Mercury 2 is stable by itself. This might be one of the reasons why it might not ionize from it. Like there's something weird about it being in a location. It might not like to do this. In the same way that Mercury doesn't like to be a single ion unless there's pairs. I'm gonna have to look that up because I have no idea why it's not even on that anyway.
Yeah, because it's not even listed on the next
Yeah,
thing. Sorry.
I mean, yeah, this is, I don't know.
It's not.
It is not something we need to worry about. evidently. That doesn't make me feel any better, like that just makes me why. All right. Variable charge. So here we have MnF2. If you were going to name that, what would you call it? Our fluorine has a -1 charge each, right? So our total negative charges is -2. So which version of manganese is this? It'd have to be a +2 charge, right? So the name of this salt would be what? Manganese 2 fluoride. Make sense? I can guarantee you there will be questions like this on the test. What's the name of this salt? Here's a salt, what's it made out of? That type of stuff, right? Go back and forth between having the chemical formula and giving the name. I give you the name, you give me the chemical formula. Guarantee you it's on there. How do I know? Because I just spent a whole bunch of time writing all this stuff into D2L, right? So it's like, all right, there we go. Because I'm the teacher. I know all the questions.
Also, it's food.
I have checked all the questions, but that doesn't mean that I remember them all. Oh, I should point out, actually, while I'm on the subject, this is the first time I'm teaching this course, it's the first time I'm using this book, it's the first time I'm using these questions. I am human, and so are all of the people that did all of the work that I didn't do before me. So if you feel like you got a question wrong on the exam, and you look it up, and like, no, I checked, and I still think I should have got this right, talk to me about it, because it's entirely possible that I'm burning through all these questions and I didn't notice that that one was scored wrong, or maybe I typed it in wrong or something. So if you're right, I'll give you credit. That does not mean that I want to know, like, I had one student one year that just wrote me an email and said, could you please explain why I got everything wrong on the test? The answer to that email was really easy. No. So don't do that. Look it up. Because a lot of them like, oh, I see what I did there. All right. But if there's one where you're like, no, wait, I looked at it. I still think this is right. Then, yeah, email me about it. Come talk to me about it. If you're right, I'll give you credit. Plus, you're not just helping your grade, you're helping everyone else who takes this class after you, because then they get to fix that question so that they don't get confused by it. You're not technically helping everyone else who's taking the test with you, because if they didn't notice, if they weren't motivated enough to check and notice, then I guess they're just okay with living with a bad grade. That because it's really a pain in the butt to change everybody's grade question by question. Because you might have been the only one who got that question this year, right? So, seriously, there's like 60 to 70 questions per chapter. All right, so, ionic charges. Once again, here is a slide that has a lot of information densely packed, right? Maybe an even better slide than that last one, because this has all of our individuals and all of our doubles and triples, right? So this might be a good slide to have, like, easily accessible. Or maybe just like a little sticky note in your book, or what page that's on or something like that, so you can flip to it quick. This is me trying to give you a few tips and hints, because I do know that 50 questions where a significant number of them are math questions, it's going to take you some time to do that. I'm hoping 2 hours is more than enough, but I'm not 100% sure.
Just acting.
Yeah, 3 days. It needs to be long enough that you can look up stuff that you're not sure, but short enough that you can't just look up every single question. I know. There's a sweet spot in there somewhere. I'm not sure where it is.
3.5 hours?
Let's go with 2. And I will say this. If everybody does poorly and nobody finishes in 2 hours, then I will adjust, right? Like I said before, I'm not here to force bad grades on you. So don't sweat it, but you know, if I find out that there's some sort of like suicide pact of everybody only answering half the questions in 2 hours, then that's no. Yeah, I'm not here to browbeat you guys. I'm here to teach you chemistry. So
If you find that out, isn't it too late?
Right.
No, if I find that out, actually, that would be considered cheating, and then we'd be talking about
No,
academic
suicide
honesty. Was that?
Suicide pact.
Oh. Okay, I meant that as a metaphor. Not as literal suicide. Naming ionic compounds, we've already done this, right? Here we have FeCl2. Chlorine has what charge? Positive, or -1 each, right? -1 each, because chlorine likes to add an extra electron. So what's that iron got to be? -1 for every chlorine. There's 2 chlorines, that gives us a negative charge of 2. Which means our iron has to be a positive charge of 2. Which means this is iron 2 chloride, right?
Oh, I get it.
As long as that confusion dissipates, that's fine. Whatever works. So, this is just going backwards. This is what I just told you would need to do, right? This slide and others. So if I give you a name, you can give me the compound, right? If I give you a compound, you can give me the name, right?
We could try.
Yeah, sure. I mean, makes sense now. I don't know how I'll feel about it on Saturday when I haven't thought about this for 48 hours, but you know, I know how it is. Well, this page doesn't actually tell you much, but here we go for some examples. Write the formula for tin 2 chloride. Let's try it. I think tin is SN.
Yeah. That's what we did.
Yeah. So tin comes in either a 2 or a 4. That should make this easy, because those are your only options, right? So, write the formula for tin 2 chloride. What is it? SnCl2, right. Because tin 2 means it has a positive 2 charge, right? And chlorine has a +1 charge, -1 charge each. So we need 2 of those, 1 tin, 2 chlorines, so tin 2 chloride is SnCl2. SnCl2. See, we got this. You got this, right?
Can you go back to the table?
Yeah?
Why is this not related to sulfide? Why is it there?
Okay, that's a good question. It says lead 4 sulfide.
Yeah.
All right, so let's work out lead 4 sulfide. So, what's sulfur? What does it want? As an ion, it is what charge? It starts in group 6, so how far away from 8 is that? 2. So that means that every sulfur atom is going to give a -2 charge. So if we have 2 sulfur atoms, what would the total negative charge be? -4. So in that particular case, 1 lead, 2 sulfur. What if the 2 sulfurs are 2 each? That gives you a -4 charge. What's the lead got to be? It's got to be +4, right?
Yeah.
And if we look back, let's double check our table. Sorry for paging through this. Is lead 4 an option?
Yes, it
Yes, it is. So we're good. That's a good thing to check, by the way. If you do it, you're like, that's lead 3. Double check, because if that's not an option, you did something wrong. So it seems like the reason there's so many slides in here is because I've left a lot of these working, well, I went too far. A lot of these work through stuff still in there. Which isn't bad. I mean, I should point out, there are practice problem PowerPoint sets. If you are confused or want a little extra practice, load up those PowerPoints and look through them. And it walks you through this stuff just like this does. Don't just read it all, try and do it, and then check the next step. Question?
The one for the map. There's one for the map.
There's one for every chapter.
Map.
Yeah. So, and they should all be there. So there's chapter X notes, and then there's chapter X. I evidently didn't keep my nomenclature the same, so it's either chapter X practice problems or just chapter X problems. Right. They are PowerPoint slides that are extra examples like this, where they say, how would you do this? And then the next few slides work you through step by step. So if you just read them, then that probably does nothing for you. But if you say, how would you do that? All right, well, let me try. And then look at the next slide and be like, well, am I doing everything right? And look at the final slide, hey, I got it right, yay! And if you got it wrong, you can be like, what did I f up? And look at it, maybe learn, not do that again, right? Question?
Okay, so with that like practice problem thing, is there a way where you can kind of correlate to like the section of like the book of the question that you're asking? Like sometimes I look at it and I'm just like, where did this come from?
Okay, so here, I'll tell you how I do this. I took the slides from the publisher, and this is what I was complaining about a moment ago, is I manually remove the practice problems that are listed as learning checks, because those are quite specifically extra problems to double check and see if you've figured this out, right? It's like, did you get it? We just talked about this. Did you get it? They already have some questions like this in the slides already that I do leave, but the extra ones that would require us to be here for 6 hours for me to go through them all on a day, chapter by a day speed, right? I pull those out and put them to the side in their own PowerPoint. So they're gonna go through, I don't like randomize the slides. So it's gonna be in order, roughly section by section, but it does not mean here's a practice thing from section 2.1 and here's a practice thing from section 2.3. But if you go through it and read, when you get to a part where you're like, I don't remember how to do this, go back to that chapter, find out which section that is, and reread it, right? But if you go through that whole thing and you're like, I got this, I'm good at all these, then that means that most of the major concepts you've got pretty well down. So if you can work through the practice problems without an issue, that doesn't mean you don't need to study, it just means that you're studying fairly well. Got it? No? Don't got it? Still believe it?
I don't believe it.
There we go. Okay. All right, so let's talk about polyatomic ions. Polyatomic ions. These are the other problem right here, the sulfites, the sulfates. All right? Polyatomic, which means they are technically a compound, because that's what a compound is, right? Multiple atoms of different types. But they are also still ionic. So polyatomic ions. Aluminum hydroxide. So we have put the hydroxide here in parentheses because that is the ion. It is a polyatomic ion. What is the charge of that hydroxyl ion?
One.
Be a bit more specific. Yes, 1, but which one? Positive 1 or negative 1? Negative 1. Because aluminum is going to be positive 3, right? It's in group 3, but it's a metal, so it wants to give up 3. So we have 3 of them right there. It told us that. So that means that each one of those hydroxyl polyatomic ions has a net charge of -1. Where do you find a lot of these hydroxyl ions? Yes, actually in medications. Once again, because a lot of medications are salts. They are ionic compounds. But the place where you find a lot of these hydroxyl ions is water. Acids, bases. An aqueous solution with a whole bunch of hydroxyl ions just floating about is a very basic solution. As opposed to one that has a whole bunch of hydrogen ions floating about is a very acidic solution. We'll talk about that later.
Do we have to?
Unfortunately, or fortunately, yes, we do. Because pH is really important in biological systems. And when we get to those chapters, we'll talk about why. And if this book doesn't cover it in enough detail, I will rant about it a little bit more.
Awesome.
Would that be aluminum 3?
It would be, except that aluminum only has one way to be. So it wouldn't be aluminum 3, it would just be aluminum. That's why we learned about how to name the easy ones first. The only time that you have to add the 1 or the 2 or the 3 or the 4 is if there's more than one way to be. Like these transitional elements in here, right? Aluminum only has one way to be, so it's just aluminum hydroxide.
Yeah, it shows it on here that it's, I got, never mind.
Perfect. Polyatomic ions are a group of atoms that still has an overall charge. The most common ones that we're going to talk about is a non-metal like phosphorus, sulfur, carbon, or nitrogen that's covalently bonded with oxygen atoms, because oxygen is weird in so many ways. Oxygen is weird, and so we can have these polyatomic atoms where oxygen is just being really what's the word for sleeps around a lot?
Promiscuous.
There we go. The non-slut shaming word for sleeps around a lot. Oxygen's just really promiscuous. Oxygen likes to make lots of friends and doesn't care. It's like, what more the merrier? It's like, can I bring my friend too? Sure! Oxygen's weird. We wouldn't be here without it, and if it was just a little bit different chemically, we wouldn't be here with it. That may not make sense to you, but that's one of those things I can tell you about like way later in this term and after class. Get me ranting about it and it'll be fun. It'll be fun for me. You're free to leave. I'm gonna start doing that if you want, like after class, whatever. That's optional. So anyway, they have a charge of -1, -2, or -3. We have the negative charge. All of them are negative except for one, which also is not being promiscuous with oxygen. It's ammonium, which is NH4 positive. That's the only positive one that we're going to be dealing with.
And NH cannot do anything with oxygen?
No, it can.
Okay.
It's just that particular all the ones that are being promiscuous with oxygen are negative. But the ammonium ion is a positive polyatomic ion. It's the only one that we're going to care about. It might be the only one realistically, period, but it's the only one that really matters for in biological systems in organic chemistry. Because if you get into inorganic chemistry, things get really weird, but we're not going to worry about that. So, here we have calcium, and here we have a sulfate ion. SO4. Now, if you're wondering, because you should be wondering, how do you take a sulfur and 4 oxygens and put them together and it only has a net charge of -2? That's a good question. And it's because these guys are covalently bound to each other in a weird way that has a lot to do with dispersed electron cloud density and stuff that we don't have time to get into. But it's a polyatomic ion. This here is a covalent molecule. Everything we've been talking about so far is forming ionic molecules, right? Ionic bonds. But that sulfate ion is a covalently bonded molecule. That oxygen is not hanging out with that sulfur because of positive negative charges. It's hanging out with that sulfur because it is, let's say, permanently with air quotes, because anything in chemistry can change with enough energy, right? But it is covalently bonded to that sulfur. And the overall charge of that polyatomic molecule is still -2, which makes it a polyatomic ion, because it has a net charge.
Okay, so anything with like the oxygen and sulfate is 8.
Yes, one example of them. Hold that thought. Because so here's sulfate, here's nitrate, right? So the question that you have is, so here we have our nitrate, here we have our chlorates, here we have our carbonates, right? Here we have our sulfates and phosphates. And yet we could also get nitrite or chlorite or hyperchlorite or perchlorite. All of these are chlorine with oxygen. So you see why I talk about promiscuous? Here we have a chlorine that's just being monogamous with this one oxygen friend. Here we have a chlorine that's having a little threesome Here we have a chlorine that's just going crazy. It's 1 chlorine and 3 oxygens, and that's not even the end of it. Sometimes you can get 1 chlorine with 4. What do you notice about the charge here? It's always what?
Negative.
Negative 1. That is not always true. Now here we have, well, let's be fair. Here we have sulfate. It is a polyatomic ion. It is SO4. It has a net charge of negative 2. When you add it together with 1 hydrogen, you get hydrogen sulfate. But the net charge is now only negative 1. Why? Because that hydrogen is bringing a positive charge with it, so the negative 2 plus 1 becomes negative 1, right? But it's still SO4, so it's still sulfate. So, here's something that should confuse you, but hopefully we can get this cleared up. So nitrate up here, that's NO3. Chlorate is chlorine O3. Carbonate is carbon O3. Noticing a pattern? Sulfate is sulfur O4. Crap. Well, we were on a roll there for a while. So 8 does not always mean 3. The 8 is actually a term that we use to recognize the most common polyatomic ion combination that we will find. So the most common carbon polyatomic ion is carbonate, and that's CO3. The most common sulfur polyatomic ion is SO4. The most common chlorine ion is chlorine O3. We call those 8s, chlorates, sulfates, phosphate, PO4. So this is another one of those things where you're just going to have to either know where to find the table, or you're going to have to remember what's the most common form. And that's the 8. You ate the most common one, because that's the one that's easiest to find. So what are the other things? What's the difference between nitrate and nitrite? 1 less oxygen. What's the difference between chlorate and chlorite? 1 less oxygen. But can we go even lower? Sure. What's the difference between chlorite and hypochlorite? 1 less oxygen still, right? So hypo means less. So chlorate is ClO3. Chlorite is ClO2. Even less than ClO2 would be ClO1, right, or just ClO, and that's hypochlorite. And what would be 1 more than chlorate? ClO4. Perchlorate or hyper, right, hyper meaning more. So these polyatomic ions, the naming for them is, it makes sense when you're like just walking up or down, right? But where you start from, that's something you either just have to know or have to know where to look at. Everybody follow? Question? Maybe a question?
No.
Unsure of a question?
I was thinking like if I found a pattern with like 8 and I did not.
Yeah. Now, you can just say 8 is 4 for S and P, and 8 is 3 for C and C, maybe? C and Cl, I guess.
So S&P.
S&P sulfate is SO4, PO4, right? So S&P is 4. And C and Cl is 3 for 8s.
Okay.
And nitrogen is just weird. Nitrate is also 3, so I guess you could say 8 is for C, Cl, and N. But it's at some point you just got to know it, right? Or know where to look it up, one of the two. Okay?
But then hydrogen.
Hydrogen by itself is just an ion. Hydride, or hydroxyl, is always just OH minus.
So would you say say it's always negative with hydroxide?
Hydroxide is always negative, yes.
Okay.
As an ion, yes, it's always negative. Out of curiosity, little quick trick. So, carbonate versus hydrogen carbonate, the -2 comes down to -1, right? Because we added an H to it. What would happen if you added an H to that hydroxide? What would you get? Right, if we added an H to that hydroxide, just like we added an H to the carbonate, it becomes hydrogen carbonate. And the charge goes down by 1. It'd be 0 neutral, but what would we call that molecule?
Which one were you pointing at?
This one up here. If we added an H to hydroxide. Don't. This is a kindergarten question.
Water.
We would call it water.
H2O.
Oh my god.
HOH, H2O.
By hydrogen.
That was,
There we go.
that was
Fast.
See? Water will frequently just split. So H2O will frequently split into OH negative and H positive. Because hydrogen is just one little proton with one little electron, and it's not very strong. It can't hold on to its electron very well. And oxygen's a big, mean bully. And so when oxygen shares electrons, frequently it doesn't really share them. And so that hydroxide molecule, sometimes that hydrogen will just be like, you know what, screw you, I'm going to go make friends somewhere else. But it has to leave its electron behind. So it's just an H+, floating around in water. And as long as our H+ is equal our hydroxides, it's still just pH 7 neutral water. But if we add too many hydroxides, we get a base that can burn you, like lime. You get too many H+, you get an acid that can burn you, like hydrochloric acid. The names of the most common ones end in -ate, one less end in -ite. The exception of those being these weird guys, cyanide and hydroxide. If you add an H to a polyatomic ion, the only thing it does is add 1 to its charge, but it's still named the same, right? So here you have hydrogen carbonate, right? And what do we call this? Add carbonate plus H, bicarbonate, or hydrogen carbonate. If you add an H to a sulfate, what do you have? Hydrogen sulfate. Halogens can form polyatomic ions with oxygen. They always have a -1 charge. Please note, I should point out, because we noticed that on that table back here, all of the chlorates are always -1. Sulfate is -2. Sulfite is -2. Phosphate is -3. So these polyatomic ions are not always -1. All of the halogen polyatomic ions are -1. But the sulfates and phosphate, like nitrates, you're just going to have to know their charges or know where to look it up. Right? Perchlorate, like hyperchlorate, has one more. Chlorite, one less. Hypochlorite has even one less than that. What's the common name for a hypochlorite solution? I guarantee you know this. I think it's sodium hypochlorite. Yeah, bleach. You use hypochlorite all the time. Well, you might not. I never really bleach my whites. I use it a lot at work, though. It's a good sterilizing solution. Don't
Also
drink it.
destroys DNA, so if you need to hide the body.
Sure. Ammonium's another good denaturing thing. Which you either know because science or because you watch. Yeah, actually, there's a lot of shows out there that probably teach you that. Yeah, like want to cover up make the Want to leave a blood stain but have it not be incriminating? Spray it but still leave it red? Then use ammonia. You want to just get rid of the redness, then that's when you need the bleach. Slightly off topic. All right, so we have a lot of shows about psychopaths on TV right now. Like Game of Thrones. 90% of those characters are, at a minimum, sociopathic.
Or CNN.
So, yeah. When we're writing these things out, the same rules apply. Nitrate ions, you can look up the charge. So if we're trying to have magnesium nitrate, what's that going to do? Nitrate has a charge of -1 as a polyatomic ion. Magnesium is going to have a charge of +2, right? So what's the chemical formula for magnesium nitrate? MgNO3. We put that NO3 in parentheses because we're treating it like it's one other atom, like it's one non-metal, right? So it's a polyatomic thing, but it's a unit all in and of itself. We do not write MgN2O6. Do not do that. That is a fundamentally different molecule. This is like, this right here is like me taking 2 football players and taping them one to each arm. That is very different than me taking those football players, dismembering them, and attaching their body parts all over you. You know, just to stay with the whole Dexter theme. Yeah, that works for that works for this, yes. With the nitrate as both the beginning and the end in this case, because the magnesium is the one in the middle. So, we put NO3 in parentheses and then a 2 after that. Because we are treating this NO3 as if it is one unit. And we need 2 of those units to make magnesium nitrate. Everybody follow? What's the formula for aluminum bicarbonate? Before I advance on, somebody do it for me. What's the charge for aluminum? +3. So how many bicarbonates are we going to need? Well, if we wanted to be really thorough, we'd look up the charge for carbonate, right? This is aluminum bicarbonate. So what's the charge on bicarbonate? -1. So how many -1s do we need to balance out a +3? We need 3 of them. So that's +3 here. A bicarbonate ion is a carbonate ion that already has a hydrogen attached, right? With a charge of -1. So we need 3 of these guys, right? So what's that going to look like? Aluminum with bicarbonate in parentheses and a 3 after it. Because we need 3. Aluminum +3, bicarbonates -1 each. We need 3 of them. Aluminum, HCO3, 3. Be careful with your parentheses. On the exam, you're not going to be writing this stuff out. So hopefully I have been careful with the parentheses. But that's what it's going to look like. Once again, this is not AlH3C3O9. That's a very different molecule. Na2SO4. What's the name? The metal is sodium, and the ion is sulfate. Now you'll note that it's still sulfate and not sulfide. Why not? I thought for these ionic compounds we change it to ide. But if it was a sodium sulfide, what would it be? It'd just be NaS, or technically Na2S, right? So we have to keep these polyatomic ions, they keep their name. But we all know, because we're so familiar with these names, that sulfate, phosphate, hypochlorate, that these guys are polyatomic ions, right? Sure. FePO4. That's a phosphate. There's one of them, and if we look it up, it has a -3 charge. So there's one iron atom attached to it. What does the charge of that iron atom have to be? +3, so it's iron 3 phosphate. Right? This is just a matter of remembering sodium only comes in one way. Iron can come in multiple ways. So you just have to remember, anytime you're naming an iron ionic compound, you have to name which charge it has. Question?
So just making sure, like, there's always gonna be like oxygen when it comes to naming compounds that are polyatomic.
Well, except ammonia,
Okay.
which is NH4,
Right.
or hydroxyl, which technically still has oxygen, sure. Most of them are going to have oxygen, yes. Sometimes, and usually quite a bit of oxygen.
If it was iron 2 phosphate, what would it be?
Good question. If this was iron 2 phosphate instead of iron 3 phosphate, what would the chemical symbol be? What would the chemical name be? Well, iron 2 has a charge of 2, right? Phosphate has a charge of 3. So that means that our smallest common denominator between those two is 6, right? So we would need 3 iron 2s and 2 phosphates. So it would be iron 2, 3, parenthetical PO4, 2. Everybody follow? Question?
Okay, if we're gonna answer this online, do we need that square?
No.
Like, I'm just trying to figure out, like, how we
The-
write out
the-
this answer.
The square, well, for one thing, once again, on the test, is going to be multiple choice.
Oh,
The square here is just to show you this is the thing. So if I were to ask you, it would be, name this compound. And you would need to recognize that PO4 is phosphate. So then you would go, well, that's iron, phosphate, but remember, iron has multiple charges. So you know the charge of phosphate, and you have to calculate, therefore, which iron it is, and then the name that you would pick is iron 3 phosphate.
so we wouldn't type this out at all, we would just.
You would
make
pick
multiple choice?
C.
Okay.
Because C might be iron 3 phosphate, and B might be iron 2 phosphate. And D might be iron 3 phosphide, which you would know is not a thing. You wouldn't pick that one, right? Or it might say, it might be a true or false question.
But there's nothing where we're gonna like type it?
Not on the exam, no. Homework, when there's only maximum 12 questions, that I'm willing to go in and double check. I'm not double checking 48 questions on all y'all. That completely defeats the purpose of doing tests online. At that point, I should hand them out to you so I can check your work and give you partial credit for your work, right? Like, there are pros and cons to both of these. So no, test is going to be multiple choice, true, false, sort of matching. Sort of matching. I don't think in this one, but there might be matching questions on a test. And if that happens, then everyone will get the matching question. But then which multiple choice, true, false ones you see, out of like the 80 some odd questions from chapter 2, you will see 12. And you will see 12. And you will see 12. And between the three of you, there might be 2 that are overlapping. And for you, it would be number 2, and for you, it would be number 9, and for you, you don't have any of the same ones, sorry. Like that's, because it's all random, so. Question?
How many questions for each chapter?
An even number of questions to get us close to 50 without going over. So, if we finish chapter 6 today, 12 of each for a total of 48. If we don't, there will be 16 of each for a total of 48, or something like that. Did I do that math right? I did that math right. It would go up. So it's just, so if we have, if you have 5 chapters on a test, then it'll be 10 questions each. So it's going to be about 50 questions, evenly distributed across all the chapters.
And it's gonna be chronological, or it's gonna be just like that?
I'm pretty sure it's going to be chronological by chapter, but within the chapter it'll be random.
Okay.
So your chapter 2 questions will come first, your chapter 3 questions will come next. I think, because I know that it will randomize within the chapters, I do not know if it randomizes your whole test. I will tell you this, if possible, it will randomize your whole test.
I don't think it's possible. But within each chapter, yes, you might get a question from the end, and then one at the beginning, and then the middle, and back to the beginning, and right. It's not going to be, here's a question about 2.1, then here's a question about 2.2. No.
I just keep them searching for all these things you asked.
Yeah. You'll be fine. You know more of this than you think you do. If you just give yourself credit. And then the rest you can look up.
Well, we just give ourselves credit.
Mentally.
I can do this.
Think positive. Calcium carbonate, calcium sulfate. We make plaster casts out of calcium sulfate. We make antacids out of sodium bicarbonate. This is another one of those things. Aluminum phosphates in it, we make antacids out of it. Barium sulfate for contrast in X-rays. Blah, 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 blah. Epsom salts, magnesium sulfate, for sucking out all those toxins, supposedly. Really just for making a really highly osmotic solution to force a lot of water out of your system, hopefully bringing other ions with it too. That's all that Epsom salt bath does, really.
You can make it into many different things.
Yeah, sure. And you could, well, yeah, it helps for a lot of things. I'm not bad mouthing it like it doesn't have a purpose in the same way that, like, you know, take aspirin and it helps, but it's just one thing and it has a really simple function, but it does not cure everything, right? So it's just like, really simple things can do good things. It's just, it's not magic. It's chemistry. And biology, which is chemistry. So it's the same thing. 6:05. We're coming up on 7:30. Do we need to take a break?
Yeah.
Let's take a break. Bathroom, stretch your legs. Whoever hits the door first, flip the light, please, so that it's brighter, not darker.
10 minutes?
Yeah, 10 minutes.
How many And all of our tests you can take it on.
You can take wherever it is that you have a reliable internet connection. And I would not suggest you do it on a tablet. Good. And if you need to, I think you can go to the testing center. You can go to any computer lab here on campus. You just can't go to the study center and have them help you with it. You might even be able to go there and say, can I use that computer back there? And they might even let you do that, but they will not sit there with you and walk you through all of it.
So why not take it on this?
Stability issues, and I honestly don't know if that's a problem with D2L, but I know that it was a problem with both Blackboard and Canvas, that stability issues between the app version, the tablet version of the integration between those two softwares. It can cause hiccups where certain questions don't get saved, or you lose connection, and then some of the answers weren't saved, or...
That's weird, I've taken everything on this and never had a problem with it.
Well, then D2L might have a much better integration.
I think it'd be worth mentioning to the class
What's that?
that when you're taking one of these exams and you click your radio button, and then you're trying to scroll down to the next question using this wheel, if the radio button is still focused, it changes your answer. And you can
It rolls
submit
it.
that. Huh?
It rolls it.
Well,
Yeah, because what you're doing is you're telling it to select this subsection, and then when you scroll up or down, it's just scrolling the answer. That is actually, yes, that is worth mentioning. So in other words, either be really cognizant of what you're doing, or just be really careful with your scroll wheel.
yeah. Click the radio button, click outside of the radio button, and then
Right.
scroll.
Yep. That's the thing. So, or just don't use your scroll at all and just always grab the bar on the right. But yeah, I imagine that's, but once again, that would actually make an iPad slightly superior because you're not, like, you're always pressing the option that you want.
Well, you're also using gestures though to scroll, and depending on how,
Yeah, I don't know how that would
depending on
work.
how they've handled that event. Isn't that lovely? I sent my mom just beautiful flowers.
teach my kids to do stuff.
Well,
I understand.
anemic.
Yeah, I understand why
Those are
we
red
give
tulips.
flowers, but and I like getting them too, but at the same time there's like this
Broken.
fundamental thing where I'm like, why do we celebrate life by handing people dead things that we just killed to celebrate? I mean, like it would be similar to be like, here's a fresh steak, I just butchered it myself. And most people are like, that's a really weird gift.
That's awesome.
But yeah, but you know,
you can let it age.
some people might be really excited by that, but there's also like, these two things are not equal. Like, yes, they are. You just took a living thing and you just killed it, and we're gonna celebrate life by watching it slowly die because it doesn't have roots anymore. Like,
And it costs a ridiculous amount.
Yeah.
And the only way I found to resolve all those questions in my mind is that as soon as she gets it, I'm gonna get this squealing call from her mom,
right? No.
and she
It's-
loves it.
Sure. It's the same thing about, you know, it's like anything else. If people like it, then get it for them because they like it, not because there's an inherent value in the gift.
So is our test under quizzes then too?
Confused
It'll
with
pop
the
up
math.
quizzes because there isn't
This
a
part I
tab
get,
for
the math
exams.
and the other math.
But yeah, it'll be
Oh,
labeled
there
as
is
an
math?
exam in the quizzes content section.
So is the one that always
It's
failed.
probably way too late for me to
I had to
get
take it multiple
accommodations.
times just to get through it.
Was that too late?
Mine says
I don't think it's too late, but it would be too late for you to get accommodations for the
Okay.
test that opens tomorrow.
Intermediate.
Yes.
Did
where I
you
did
do
get a B.
mine?
And I didn't
I have not yet because none of them have been
It's
activated,
algebra.
but
It's like when
I am
it's
aware of
happening.
yours, yes. And I will have to fiddle with how to make it do that for you. I'm pretty sure I know how.
I finally got
It's like,
Just the time.
after I banged
right, but there's like a
it was like every tutor
specific
session,
user
every
has
session.
different things option, and I just haven't activated it yet. Because I haven't finished it.
That's what it took.
So, and I will finish it tonight after I figure out if we finish this chapter.
So much.
So,
I wish I
it's
loved
possible
it, but I
to request
because if I loved it.
my accommodations in double time
I
and
have a career
quiet
as a financial
testing
advisor.
environment.
Quiet's up to you.
If I loved math.
Well, I go to the testing center.
Or a
Right,
banker.
yes. You choose the environment when it's an online thing.
A chemist.
Accountant.
And
Theoretically,
I
no.
don't know.
Asking for a pretty please is not, because I have to, if I did that and then somebody else found out,
Sure.
that would be a problem. But the moment that I do have official recognition, then yes, I will do so. I have no problem with the act of doing so, it is simply a matter of equity.
It got a lot better when I started digging into value because it wasn't just the ADD, it was the anxiety.
If you do it first thing in the morning tomorrow, then, and then give me the day, so don't take it till Saturday. If I get a letter tomorrow, then yes, I could add it. But
Yeah, I'm going to.
I just don't know how fast they're gonna get around to
Right.
notifying me. And so that's the lag that I can't control.
The lag I think that's the biggest is if it's not payroll.
Right. And so the problem is, even if you start it tomorrow, if they don't finish it by the end of day Friday, I'm not gonna get it before the test closes.
Usually when I submit mine, it's pretty quick, they just have to click submit and then they just forward it on there.
I forgot that, I've been out for almost a year and I forgot that I actually have to
Did you say at the
re-register
beginning of
with
class if you were able to grade the
the-
homework?
Oh, you've got it.
I did grade and correct all the homework, yes.
Okay.
Actually, let's,
I was trying to look earlier to see if I could look at the.
well, because we weren't sure, 55, we're only about halfway. I need to hurry this up. Let's see if I can reload, what does it do?
That's good, because I didn't.
50% is 4.
No, it's horrible, but compared to what I did, that's
Nope,
good.
it still hasn't auto-graded, so I'm gonna have to find out why it's not doing that. So you should be able to go and look at it, but it has not finalized your grade in the grade book, and it should have. So I don't know what I didn't click to tell it to do that.
So once that happens, maybe we'll be able to go in and see.
You
what
should be
we
able to go in and
missed.
see it now.
Well, but I wanna know what I
What you got
missed.
wrong?
Mhm.
That I'm not
Yeah,
sure
it's
of.
not showing that, but it finalized my grade in the grade book.
None of my grades are finalized in the column in the grade book. It's acting like I need to grade them, even though I have graded them.
Oh, huh, that's weird, now it's not.
Right.
Sorry.
So I don't know what's up with that.
Is there something we could do, extra credit, something?
That's weird, it showed up earlier now.
I know.
So if we don't finish 6 tonight, will that
It will not
carry
be on the
over to
test.
the next exam?
It
though?
will.
If we don't finish 6 tonight, then the test will be 50-ish questions over 2, 3, and 4. And the next test will be possibly over 5 chapters instead of 4. So, right, yeah, it's like, there's really not a, like either, there's strengths and weaknesses to both, right? Like, not having it today, you might like, but it means you're gonna have more questions over chapters that are all about math. And it means that you're gonna have more material that you'll need to be able to cover, but fewer questions for each one, but more, so it's like,
You could probably get through 10 pages by 8 or 9 o'clock.
I mean, if we keep going and I don't get too distracted, I think we'll probably be okay.
So no
Yeah.
more questions, y'all.
Well, but you
I
said that there was
posted
a lot of
a
people
link
that answered some questions.
Right, yeah, exactly. I mean, we're
The
moving
YouTube
through, it's just a
list.
matter of,
Okay.
do we get there? That's
And,
the-
I need to figure out.
right now, I'm
Hey, so I emailed.
uploading raw video,
Okay.
you know, not beautified.
About what?
That's
I think you
Like
have
the
it,
first time I
Um,
submitted it,
and then,
As
so
long
when
as
I
there's the
click on
audio,
your, like on
you know,
the actual biology homepage and I click email
Thank
you,
you.
it won't,
but it's gotta have the
it won't
thumbnail
email
and
you.
the
It said it
face.
sent, but it
I
never
don't guess.
responded.
I don't think I got anything about
But it did that to my, so I'm taking
What
a
did you
different one
ask?
too. It was
Just-
about my homework.
just a specific question about the homework.
I don't know, I don't remember.
Yeah,
honestly.
I don't remember getting a question about the homework now.
Okay.
But that's the way you're supposed to do it. You're supposed to email me through Cougar
Did you
Track.
get my
Yeah.
email today?
Layout sequence,
I think I did
trying
get
different things.
I almost
And each
emailed
time
you,
you
but
get
I was
done,
hard on the way, so I was
Yeah.
like, I'll just do 5 minutes
Like
later.
5. I did not take into account that the target file is supposed to be 18 gigabytes.
But,
From Kelly.
I got a
It
head
creates at least 3
So-
times that amount
I literally,
of
I literally had to read.
I didn't send it from my computer, I sent it from my work.
and deleted.
Well, it shouldn't matter which one you sent it from, as long as you sent it to my Cougar. But if I responded, I would have to respond to you in Cougar.
Yeah, it's on.
So,
What does mean it's been so long?
I think there's like a problem.
Kelly Farber?
Yep.
Yeah, I got that one.
Okay.
But,
It just got pulled.
that's the only student email I have, so I don't know.
Maybe there's like some problems.
You emailed me as well?
Yeah, I don't think that it works when you click on his
Email me.
email me.
Yeah, that's what I
It
was.
does not seem to be.
But see, when I go into
That's
Cougar
what I
Track
feel
and I try to put your name doesn't even pop up, so I don't know what the deal with it
I
is.
clicked the email me and it worked. That's how I found it.
Did you click, well,
Through,
we'll try. We need to figure that out, because you do
Because I
have.
did it to my other teacher too, and she never got it. So I
Yes.
actually went to her email that she had sent me before classes started and then
Responded to
emailed it
that.
from that.
Which we could
They're
also,
not in there.
which I could just send an email to everybody, and then you could just reply to that with questions. That would also work. But you should be able to just click on my name on the web page, on the page for this class at a minimum, and it should get to me.
Yeah, that's
Because
what,
that's the whole point.
that's
So-
what I was thinking.
So, no, I did get yours about this evening, but, and I got quite a few before class started, but I have not really gotten anything since. No. So we do need to figure that out, because I need to be able to get that so that I'm appropriately assigning attendance and all that jazz. Wait. Are we missing, is Maggie the one we're missing tonight? Yeah, that must be it. Okay, so, because yeah, like I've got it on my phone. It's got its own special little app just for effectively you guys and the boss people trying to email me to tell me what to do. So it's not even like it's getting buried in the 100 emails I get from Mizzou every day. It's like, no, it's just all by this.
Okay.
So do you know if that guy that came in here that does the study,
Tutor sessions, yeah.
is he not a teacher no more?
No, I think he just runs that study section actually from what he described. I'm not sure. He might.
That was my chemistry teacher before I got
If you
that.
choose to email us,
Oh,
it was bad. Email us as the tutor. No, I've talked to him.
As a reminder of that.
Yeah.
Yes, I still have the handout, so I could email you a reminder of the tutoring information.
Okay, that sounds perfect, yeah.
Which I could also, I think I have 2 of them up here, so I could also give you a handout if you remember to ask me before you leave.
No, handouts aren't good. They get buried in purses and backpacks.
Yeah, okay. True, I can see that. I can see that.
On my first pass.
Alright, so let's see if we can get through this, and if we can, I can spend some time after we're done, or if we can't, I can spend some time after we give up, talking about
Too organized.
the homework and stuff for tomorrow, or for the test this week. So, here's the thing. Molecular compounds. This is carbon dioxide. Now you'll note that we are giving it a name, and now you'll see that little dye in front of it, right? Now when we were talking about our ionic compounds, we didn't give dyes, tries, we didn't name things in terms of numbers as part of the name, because we were supposed to understand that this was an ionic compound, and therefore we should be able to intuit how much of each is there based on our knowledge of the charges of those individual components. When we start talking about covalent modification though, like phosphate, which is a covalent molecule, covalently attached connected molecule, those guys we need to have some way of knowing, either by nomenclature or simply because we know what phosphate is, because it has a common enough name that it gets its own special name, that we know what's in that molecule. So, from 6.5 what we're going to be talking about is what the type of things that we're dealing with when we're dealing with covalent modification, covalent bonds. So instead of atoms hanging out with each other because they're attracted to each other as a positive-negative associations, now we're going to be dealing with atoms that are holding on to each other, that are hanging out with each other because they have agreed to share electrons. The goal is still the same, filling up that top shelf, whichever shelf it is, right? Making sure that your shelf is full. But it does not necessarily involve the creation of ions. Most covalent molecules are in fact not going to be ionic. They might be polar, there might be some different charges here and there, but they're more than likely going to be neutral in their charge, positive, negative type stuff. Covalent bonds. We're sharing electrons to fill our valence shell. I've already said all this. Moving fast. Ish. When we name this, the first non-metal is named by its element name. The second non-metal is named with the first syllable of its name followed by an "ide" there, so there we have our "ides" again. So that would make me, my earlier gonna say yes, wrong. When we have a subscript ending two or more, prefix is used in front of the name, so mono, hexa, octa. You guys recognize this, right? Mono, di, tri, tetra, penta. Right? So here's nitrogen, because it's the first one. Dioxide, because there's two of them. Here we have nitrogen with 3 oxygens, so that makes it trioxide. Now this is not nitrate as an ion, this is nitrogen trioxide. Some of our nomenclature here is a bit, when vowels O and O or A and O, what? O and O? O and O and AO?
The first one gets.
Yeah, we omit the first vowel. It's like, if we're naming a molecular compound, mono is usually omitted. We usually don't say like nitrogen monoxide. It's just nitrogen oxide. Nitrogen dioxide, though, if there's 2 of them, we would call it dioxide. The exception here is carbon monoxide. Why? Because carbon monoxide is special. We care about carbon monoxide. Carbon monoxide can... Honestly, I think some of the exceptions are just because it became so common to name things something, even though scientists would say, that's not right, you shouldn't be saying that. Everybody would go, but that's what we call it. If everybody calls it that, then why don't we just call it that? Take care of it. Fun. There are other examples of things that are named wrong
that if scientists had their way, they'd be like, you should not call it that. Like, organic food. Don't call it that. But no one's going to listen to me, because it's too, everybody knows what organic food is. Here's the thing, the only organic chicken that's not organic is a rubber chicken. And even that would be organic if it came from rubber that actually came from a rubber tree. Dang it, it'd still be organic. I don't care how many steroids you pump into your chicken, it's still organic. But that's not what they mean when they talk about organic chicken. They talk about no pesticides, no herbicides, free-ranging, perfectly all natural, no GMO. Sorry, that's pet peeve of mine. Alright, so what do we have here? Some common molecular compounds, especially in biological systems: carbon dioxide, carbon disulfide, dinitrogen oxide, N2O, as opposed to nitrogen dioxide, which is NO2. Why does the nitrogen come first? Who comes first in the periodic table? From nitrogen and oxygen, who comes first? Nitrogen.
So what do we call the nitrogen oxide, nitrous oxide?
Nitrous oxide. I don't know, the same way, why do we call the stuff that you put in cars that blows out the engine and makes it go faster, we just call that nitrous. That's not nitrate. I don't know what nitrous actually is, other than the thing that Fast and the Furious has taught me. It's the stuff you push in the thing to make your car go faster. And video games have taught me that that also damages your engine.
How education?
Yeah, exactly. The things we learn from TV and games. Not always correct. Frequently wrong. Sulfur hexafluoride. 1 sulfur, 6 fluorine atoms. Don't try and count the ionic charge of this, because that's not the point. This is a covalently modified, covalently attached molecule. That is 1 sulfur sharing electrons with 6 other fluorine atoms. Not necessarily all of them with the sulfur, I should point out. But they're all sharing electrons with each other, forming one molecule where you cannot remove something via ionic interaction. Covalently attached atoms. Sulfur trioxide, manufacture of explosives. Lots of fun stuff. What's this? What's the first one? Nitrogen. Tribromide. Tribromide. Right? Nitrogen, no prefix. Bromide, but there's 3 of them, so we give it a prefix of tri. So we use the first nonmetal, comes first. Bromide with the first initial followed by I, bromide. Nitrogen, tri-bromide.
But see, Br is bromine, so then you have to add the IDE also?
Right, so you take the first syllable, bromine, brome, make it I instead, bromide. Using the first syllable of its name followed by ide. So that would make something americunium would be something other amoride, right? But you're never going to see that because americunium doesn't last very long. But like, that's an example of where the nomenclature is a little weird because like, yeah, but amoride for americunium, that was first syllable plus ide. What's the molecular compound for diphosphorus pentoxide?
P2 for di, right?
Four?
4 is tetra. Pent is
8, no. I don't know.
5.
5.
I was thinking, but then.
P2O5. Now, once again, this works, this nomenclature works when we're talking about relatively simple molecules. We get into the organic chemistry portion of this class, and the nomenclature is just going to explode. I'm just warning you. But that's like last third of the class. No. You signed up for it, it's in the learning objectives. Besides, that's where the fun stuff happens, is in the organic chemistry. A compound is usually, here's some rules to tell the difference here, it's usually ionic if the first element is a metal, like NH4. What's the name that we gave to that NH4 ion? Ammonium. K2O, K is a metal, potassium oxide. There's our ionic potassium oxide. It's molecular if the first element of the formula is non-metal, like nitrogen, carbon, phosphorus, sulfur. Once again, when we go through this on the quiz or on the test, this is going to be multiple choice. So find the answer that fits. Look up the rules if you need to and find the answer that fits. Here's the flow chart! This might be handy. It's a lot of information in one slide, right? I don't know if it's actually handy. You'll have to tell me after the test if it was handy. Flowcharts are really useful for some people, really not useful for others. It just... Alright, 6-6. We've got to get from 6-6 to 6-9. Lewis structures. We're talking about covalent modification here now. So, these dot structures, we've seen that before, right? What do the dots symbolize? What do the dots represent? The books on the top shelf, right? The valence electrons, right? And because we're keeping things simple for this class, what's the number of valence electrons that fit around any given atom? 8, right? That's where the octet rule comes from, at least as far as we're going to apply it. Now, that means that we can draw it like this. How many electrons does carbon have? Look up there, it's in group 4, so how many valence electrons does it have? 4. Because it's in group 4, that means it has 4 valence electrons. Lithium has 1. What is it, B? Beryllium? BE? What was that? Beryllium? Yeah. Aluminum has 2, boron 3, carbon 4. So, why do we have 8 around it? What do each of those hydrogens bring? They bring 1 electron, which means that that carbon is surrounded by how many electrons? All 8. That makes it happy, right? That makes it stable. Why is the hydrogen happy when it only has 2? How many shells does that hydrogen atom usually walk around with? 1. Just 1. And how many electrons fit on that first shelf? 2. Only 2. So that hydrogen is perfectly happy sharing 1 electron with the carbon because the carbon's sharing 1 electron with it, and since they're sharing, they both get to count it. So the hydrogen says, look, I have 2! And the carbon, because he's got 4 hydrogens around him, is saying, look, I have 8! And everybody's happy. If we wanted to name this carbon tetrahydride, we wouldn't call it that. What would we call it? We wouldn't call this carbon tetrahydride because it has a very special name, especially when we talk about organic chemistry.
And fuel, we call it methane. Methyl. CH3 is a methyl group. CH4. Alright, what about this nitrogen right here? That nitrogen has how many electrons around it?
5.
Well, nitrogen over there, normally it starts with 5, yes. So how many electrons does it need to make 8? 3. That is why it is sharing with 3 hydrogens. So if we were to draw the dots around that nitrogen, the first 4 would go 1 on each side, and the 5th one would go, pick a side, it doesn't matter, right? And so that would mean that we would need 3 hydrogens to share on the 3 sides that only had 1. And that would once again give us nitrogen with 8 around it, and 3 hydrogens with 2 for them, so everybody's happy, and that makes it a stable molecule. What's the polyatomic ion that we're used to talking about? Not NH3, but what? NH4. And what's the charge? +1. How could we get that? Do you see it? Let's take a hydrogen ion. Just a proton that doesn't have any electrons to play with. What if it comes up and says, hey, Mr. Nitrogen, you've got those two electrons right there, and you know, nobody else is sharing them with you. Can I just kind of hang out next to that and maybe sort of share them with you a little bit? Is there room for it to fit there? Yeah? Is there another atom occupying that space? No. Now, could a regular hydrogen atom come in and do that? Not if it has its own electron already. Because that would mean that the nitrogen would have 9 electrons surrounding it, and that would not work very well, would it? But a hydrogen ion could, H plus could, and what would that make the overall charge of that NH4 polyatomic ion be? +1. Oxygen combined with 2 hydrogens. Once again, if we wanted to, we would call that what? Oxygen dihydride? Maybe? We don't call it that. What do we call it? H2O or water. Right? Dihydrogen oxide, I guess. H2O.
The hydrogen monoxide is the one they use for the...
For the side of the thing that nobody understands, they're just talking about water. The threats. Dihydrogen monoxide. Oxygen, over there in group 6. How many electrons does it need to fill up its outer shell? 2, right? So if it shares electrons with 2 other hydrogens, it has 8. And those hydrogens have 2. Now, that's the Lewis dot structure, but we can also take all of those we can take those pairs of electrons on one side. So those 2 guys right there, that is the bond that is shared between that carbon and that hydrogen, we can write it a different way with a line. And that signifies that it is a single bond. That means that both of those atoms are sharing 1 electron each with each other, forming a single covalent bond. Which means all of those hydrogens are attached to that carbon via a single covalent bond. It means all of those hydrogens are attached to that nitrogen via a single covalent bond each. If I'm going to name them by specifically calling it a single covalent bond, that implies that there is something more than a single covalent bond. Otherwise, I would just say that there are just all covalent bonds, right? We can get double covalent bonds. We could even get triple covalent bonds. We could even get sort of. You can't really get a tetra bond. Well, not with carbon. You can get really weird bonds later, especially with some of these transitional elements that get to be really hokey with what you call a valence electron, right? We're not going to worry about that. I'm just letting you know it can get hokey. Here's a space fill model instead of the Lewis dot or the stick model. So here we have our central carbon surrounded by 4 hydrogens. Here we have our central nitrogen surrounded by 3 hydrogens. Here we have water surrounded by 2 hydrogens. I want you to notice something. Take a close look at the difference between the methane space fill model and the ammonia space fill model. Because we're going to get into this in a minute. What's the difference?
There's something missing in that ammonia model at the top, right? Now, why is it that those hydrogen atoms are spread out like that on around that carbon? Because those hydrogen atoms are carrying electron density. So they have their positive proton center, there's electron density between them and the carbon, and so all of those negative electrons, they don't want to hang out really close to each other, right? They want to get as far apart from each other as they can around the surface of that atom, and they will do so by forming a very specific orientation, which we will give a name to here in a minute. Why don't those three hydrogens, why are they all on the bottom like that? Doesn't that mean that they're closer to each other? Like, because they're not just on the side, right? They're not just like blip, blip, blip on the side like a plane. They're below the plane. They're all below. If you were to cut that atom in half, sort of like that, they'd all be below the cut. Why? Do we have some negative density right up on top here that's pushing them down? Just like we had some negative density right up on top here with that hydrogen that's pushing them down? Yeah, we do. That electron pair that's not being shared with anyone else because it's already a pair, they're sitting right on top of that dot. We don't draw them in a space-fill model, but they're there. And that's why those three little white dots are not on the side of the blue ball, they're down near the bottom, just like they are around that black ball. Because there's still electron density, there's still negativity that's forcing all of those other pieces to move in certain directions. And that is because we are single bonding all of these molecules. If we start talking about double bonding, the jig is off. Other shapes start applying, and we're not going to get deep into the hybridization things, and I really wish we did, but we're not going to. So, covalent bonds is when we share one or more electrons with another atom. And this second bullet point here is kind of important. Valence electrons are shared by non-metal atoms to achieve stability. Metal atoms are nifty in the way that they form their lattice structure and their crystals, which is why when we talk about ionic crystals, it almost always, if not does, always involve a metal of some kind. Metals don't have to form ionic bonds to pair with each other. They're weird like that because of the way their electron density works out. Like a big chunk of copper, a big chunk of iron, that's not a whole bunch of iron molecules covalently attached to each other. That's just a whole bunch of iron molecules just hanging out like so. Just chilling. But non-metal atoms, will form covalent bonds to share electrons to fill up their outer shells. What's the thing about non-metals that makes them so different from the metals over here on the left, other than the shiny bit and the ductile bit? What's one of the major properties of metals that we use them for, that we find them so useful?
Conductivity.
Conductivity. What do non-metals not do very well? They don't conduct very well. That's because in our non-metals, when we're combining them together, we are forcing those electrons into very specific relationships to form those covalent bonds. The reason that the metals, whole metals, conduct electricity really well is because their electrons don't really have specific places. They can shift anywhere and all over the place. That's what electricity is literally the flow of electrons. From one atom to the next, 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 to the next. These guys, these nonmetals, they don't conduct very well. Especially in compounds, because we have locked their atoms into place via covalent bonds. Hydrogen. Normally when we talk about hydrogen, we talk about hydrogen having one proton and one electron. But that is not stable, because its shelf, is not full. we still work? Did I break it? No, I didn't. Good. Its shelf is not full. But if it shares its one electron with another hydrogen, now both of their shelves are full. This is why hydrogen as a gas is never found as H. It's found as H2. Chlorine, bromine, iodide, as in their natural occurring state, as a pure element, what shape, what form do you think they're going to take as well? They're missing one electron to fill up their outer shell. So just like hydrogen only needed to share one to fill up its shell, what if each of them, what if chlorine and chlorine decided to share one electron with each other? How many electrons would there be around the outer shell of each? 8. The halogens are usually found in diatomic atoms, or diatomic molecules. 2 of them. H2, Cl2, Br2. Now you can find them individually in molecules where we've covalently modified them, broken up that pairing. You don't always have to have 2 bromine atoms in every molecule. You can have just 1 bromine. But if you're going to talk about pure bromine, you're talking about Br2. If you're talking about pure hydrogen, you're talking about H2. Why are we not also therefore talking about Li2 or Na2 or K2? Because even though hydrogen's over there all the way on the left, what do we call everything beneath it? Metals. And what do they look like at room temperature? Solids. What's hydrogen at room temperature? A gas. Very different. Here's the thing. 2 hydrogen atoms that are far apart with only 1 electron, the energy level that those hydrogens have is rather high. The reason why they share, and this is a conceptual graph here, but this is foundational. So I'm going to spend a minute harping on it. Hydrogen atoms that are individual and separate have much, much more energy than a hydrogen diatomic molecule. In the same way that water at the top of a dam has much, much more energy than water at the bottom of a dam. And the thing about all of reality, and I realize I'm bringing in a player here that this book is trying to avoid, but entropy is not a nice guy. And entropy is part of a physical process that says every atom will seek to find the lowest potential energy state that it can occupy all the time. And that is why you do not find hydrogen atoms floating around with 1 electron by themselves. Because entropy will, then every time it finds one and says, "Go get it, friend!" Because you have too much energy. Now we can force them to be alone. And what does it take to do that? A lot of energy. You guys remember chemistry? Like, did you take a chem lab in high school? What did you have to add to almost, not all, but almost every reaction that you ever played with, messed with in chemistry class?
Water.
Sure, most reactions are aqueous. Past that, what was beneath the water?
Heat.
Heat. It's a lot of math.
Yeah.
A lot like this chemistry class. This is foundational. It's also conceptual. The reason why you find these hydrogen atoms in this configuration is because that's the lowest energy state that they can find. If you could provide a way for them to get even lower, they would do it. And you wouldn't have to do anything to help them, other than provide them that opportunity. They would do it. Now, to get them to go the opposite direction, you have to force it. Forming these bonds makes them have a lower energy state than what they started from. Plants take hydrogen from water, oxygen from water and carbon dioxide from the air, pretty much just carbon dioxide from the air and hydrogen. And they combine it into sugars. But what does it take to do that? A whole bunch of sunlight, which means a whole bunch of energy. What do we get by burning the sugar that we get from plants? A whole bunch of energy. Lewis structure. You want to arrange them to give octets, except for hydrogen, because once again, that first shelf only has 2, right? So, our shared electrons are bonding pairs, 2 dots, or a single line. Non-bonding pairs, or otherwise known as lone pairs, are just placed on the outside somewhere, it doesn't matter where. So here we have fluorine. We've lined them up to make it really obvious that they're going to orient themselves in this manner. And they will come together to react to form that structure there, which we could draw like that with a dash instead of just 2 shared dots. We could also represent that just by F2. And if we used a space fill model, it would look like that. 2 big circles that are together. Yes?
What about the noble gases, like helium and stuff like that? Do they fall into that category as well?
Well, what category? What do you mean?
Like the...
Always being diatomic? Why would they? The whole reason why hydrogen is forming a diatomic molecule is because it needs to share electrons to fill up its shelf.
Okay, so those don't need to...
Yeah, their shelves are all full.
Okay.
So they're just there. Sitting there, being all noble. These are the guys that exist as diatomic molecules. What do you notice about the state of all of these things at room temperature? Gas. Okay, fluorine makes sense. They're sharing 1 electron. What would oxygen have to do to fill up its octet so that both of those oxygen molecules had 8? What would they have to do? So here's our oxygen. Here's our oxygen. Each one has how many?
No, 8.
We want 8. Each one starts with
5.
5.
No, it's
6.
It's in group 6, so it starts with 6. 1, 2, 3, 4, 5, 6. You see how I'm drawing it? I'm not drawing it vertical. I'm like tilting it off, 45 degrees. Follow? 1, 2, 3, 4, 5, 6. If we share this guy and this guy, how many would each of them have around them? 8. That would not be a single bond. That would be a double bond. Alright, let's take that lesson and ask, how does nitrogen form a diatomic molecule? It starts with 5. So what would it have to do? I'll give you a hint. It's really hard to draw with a Lewis dot structure. It needs 3 more. Each of them needs 3 more. So what would it have to do? To get 3 more, it'd have to share 3 of its own, right? So that would mean that that nitrogen, that N2 right there, how many bonds? It's not a single bond, it's not even a double bond, it's a triple bond. This is why, even though nitrogen is 70% of the atmosphere, plants need nitrogen for fertilizer. Why? It's 70% of the freaking air. Can't they just take it from the air?
Has to be fixated.
We have to fix that nitrogen, and that's a nifty term that we use to describe what? Taking that N2 and breaking not just 1, not just 2, but all 3 of the bonds that's holding it together, so that we can get a nitrogen molecule that's available to incorporate into biological molecules. Guess how easy that is? The answer is not easy.
It's from bacteria.
Certain bacteria, certain quite a few fungi. Most organisms can't fix nitrogen. Even though you breathe it in every moment of your life, 70% of the air around you, you butt kiss with it. There are states that are thinking about using it as a method of execution. A gas chamber with nitrogen. Put a man in a room, fill it full of nitrogen, and watch as they suffocate. Because there's no oxygen. It's one way to kill somebody.
That's cool.
I mean, we could that, or we could shoot them in the head, or we could inject them full of drugs that have expired and no one will sell it in the States, which is why there's this issue. But that's politics.
They should start nitrous oxide, laughing,
Yeah, there you go.
die
Well,
laugh.
that's the idea behind some of the drugs, is let's knock you out first and then kill you. The problem is getting the drugs, keeping them on. That's why there was a month ago, there was a state that was trying to kill like 5 people. Like, do it fast, do it fast, do it fast! Because somebody realized, holy, this drug expires in a month. And you can't use expired drugs to kill people. That would be inhumane. Right? I don't want to get too deep in the politics. I'm just throwing it out there. You guys can argue with that over coffee. Because you're college students, you stay up all night drinking coffee, right? All right, let's keep going. So, drawing Lewis dot structures. Here's our carbon with 4, here's our hydrogen with 1. We put them all together to form that nice little methane. And that gives all of these guys the electrons that they need to be nice and stable and happy. You've seen this already. Methane, ammonia, water. What's different about that water molecule and that methane molecule? Remember I told you that that ammonia molecule is just missing that little white dot at the top, but it's still that. The reason that those 2 balls are pushed off to the side and down, right, is because we have those two dots are still there. What about oxygen? Why are those 2 hydrogens pushed off to one side? Because guess what we have? We still have 4 sets, right? They're just 2 lone pairs. But they are still negative, and they are the things pushing the 2 hydrogens to one side.
So is ammonia at all considered polar like water is?
Yes. Well, yes.
That's why it's reactive.
Hmm? Which will, if you don't understand that question, we'll get to it. Hopefully soon. So, a double bond, we've mentioned, that's when we share more than 1 pair, right? If each atom is sharing 2 electrons instead of just 1, it's a double bond. A triple bond is when we're not just sharing 2 atoms, or excuse me, 2 electrons, but 3! There's your triple bond. Draw the Lewis dot structure for carbon dioxide where the central atom is carbon. So, how many electrons does carbon have around it? 4. Carbon is in group 4, so it has 4. 4 valence electrons, which means we would draw the dots where? How many on each side? 1 on each side. Oxygen is in group 6, so it has how many valence electrons? 6. So it would have 2 lone pair, right? Because we put 1 on each side to get 4, and then we put 2 more dots on 2 sides to fill it up, right? So we have 2 lone pair. Those guys are not going to get involved in this. Because they're already paired up, right? But oxygen does have 2 single electrons, right? So it's going to share both of those electrons with our carbon. Each of them is going to share both of those electrons with our carbon. So what's that going to look like? How many bonds are involved here? 2 on each side. Here's all of that we just did, written out. Valence electrons 4 here, valence electrons 6 here. They're totaling them up there, because that's nifty. I don't know what you would actually, I mean, that's a nice number to have, sure. I don't know if we're actually going to use that here in a second. So here's what we have. Our carbon, all 4 electrons are being shared with oxygen. A double bond. double bond right there. Why is that? So we've drawn this up here. We're going to attach one single bond, so we have oxygen attached with a single bond to carbon. Why are we not done? Let's walk through it the way they're walking through it. Attach each bonded atom to the central atom with a pair of electrons. Right. Carbon still has another atom, another electron on top and on bottom, but so there's two more that aren't paired up, right? There's one right here that's not paired, one right there that's not paired, right? And oxygen has the same problem, right? It's got two lone pairs out here, but it's got another one on both sides that aren't paired. So what do we have to do to make sure everybody has 8? We have to share that extra set to form a double bond.
Where do those come from?
They're coming from the dot structure that we have out here. So here, let's try.
Okay.
So, oxygen, carbon, oxygen. So I'm going to tilt this like this. I'm going to tilt this like this, just so that you can see what I'm doing, right? So oxygen has one here, and over here it's got a double and a double. You follow what I meant, why I tilted it, right? Same thing over here, we'll have a double up here, a double over here. We'll have one down here and one on this side. Now carbon has 4. One on each side. So we can share one of them so we're now linking these two right here and these two right here. That is what happened right there. They're just not drawing all the dots for you. Alright? But that means that these two count over here, but now our oxygen only has 7. And this oxygen gets to count that one, but that means it only has 7. And this carbon gets to count that one and this one, right? So if I draw a little arrow down here just to give us the carbon, that carbon would look like this. There's 2 of them there. Actually, let's put them on top because that's where I drew it. 2 of them on top. There's 2 of them on the bottom, right? But we have one on the side here and one on the side there. That carbon is not happy yet. What would it need to do to get one more electron on both sides to fill it up? Well, it needs to share another electron. Conveniently enough, both of those oxygens have a spare, don't they? So this guy can get shared with that. This guy can get shared with that. And now we have formed, now what's happened to that carbon? It has all 8, it's happy. We would draw that as a double bond, like that. A double bond between both oxygens and the central carbon. Each oxygen is sharing 2 electrons with the carbon. The carbon is therefore sharing all 4 of its electrons with someone else, split evenly between the 2 oxygens. Does that work?
Carbon has 4. And hydrogen has 1. No.
Because the carbon has 4 because it's like, is it because it's a 4-way percent and...
Carbon has 4 because it's in group 4. And it wants to get to 8. Right?
Yeah.
It has 4 valence electrons.
But hydrogen only has 1.
Hydrogen only has 1.
So if you do 40 between that, you don't need hydrogen. You just need the C2.
Let's erase those carbons. Alright, and now let's focus on this carbon right here, right? So that carbon right there, see, I'm blocking it for a minute. That carbon right there has 3 bonds. It starts with 4, right? 4 electrons. We're sharing 3 of them with someone else, right? So let's write in our shared ones with S's. We're sharing this one here, that gives us a pair, right? We're sharing this one here, that gives us a pair, right? We're sharing this one here, that gives us a pair. There's our triple bond with that other carbon. Do we have 8 yet?
No.
No. We need to share that one right there with somebody too, don't we? Well, who's a convenient guy to bring along just one little extra electron? Hydrogen. So yeah, that is an example of a perfectly valid organic molecule of 2 carbons triple bonded to each other and 1 hydrogen on either side. And if you followed all of that by using the Lewis dot structure, then good, you're picking this up. It is simply a shorthand to help you count the number of electrons. And with the exception of hydrogen, everything else wants how many? 8. And you will form as many bonds as is necessary to get 8.
I thought fluorine, you could only do like 2 and stuff like that. Or is that,
Fluorine, okay?
or oxygen?
Oxygen, we did oxygen, but let's do fluorine. So fluorine has how many electrons? 7. 1, 2, 3, 4, 5, 6, 7.
Oh, okay. I see it now.
We're missing 1. What could we do? Well, we could bond with another fluorine that has 1 there, but all of the others. Well, sorry, shouldn't confuse you. 1 line, right? Single bond. Not everybody has 8. And we're happy.
And how would you write that?
How would I write that? Well, you could write it like this.
The F2?
Well, yeah, just F2.
Okay.
Yeah. Yeah, F2. Just like H2, Cl2, Br2, I2.
So
Yeah.
other than hydrogen, everything else is 8?
Yes. Hydrogen is weird. Technically helium is also weird, but helium we don't worry about because it's a noble gas. But the reason it's weird is because that first shelf, that n equals 1 for the quantum state, that bottom shelf only has room for 2. Everything else has room for, let's say, 8 in air quotes, right? Because 4 and up, a lot more than that. So does this make sense? Do we all follow how to do that? We're probably not going to finish this.
You're not.
Exceptions to the octet rule. While the octet rule is useful, hydrogen requires just 2. The noble gases are weird. They don't do anything. Non-metals like potassium, sulfur, chlorine, bromide, iodine, they can form compounds with 10 or 12. So the octet rule works except when it doesn't. And that's why the octet rule is a very simple way of modeling bonds. Some of these guys are weird because their valence electron... Effectively what happens is some of those books on the lower shelves, if you give them enough reason, they'll start sharing with other things too. Instead of just the books on the top shelf, some of those lower shelf electrons will also be able to be recruited into bonds. We're not going to talk about the whys, but here's your exceptions. So these guys are weird, and sulfur is weird, which is how you get SF6. Because sulfur can have up to 12 valence electrons and still be handy, still be comfortable. So these are exceptions. What do you have to do with the exceptions? You just have to know them. Or know where to look it up. Exactly. Chapter 6 is a big chapter. It's okay. If we don't finish it, that's fine, because octet rules, it's very simple, but it is a good way of learning how these things are put together, how we start building simple molecules. But let's see if we can get through this. Electronegativity. This is another characteristic of atoms, just like atom size, right? Or ionization energy, right? Electronegativity is something that we haven't defined yet, but we will in a second. But we're showing you that electronegativity is increasing as we move through the period, and it is decreasing as we go down. What is that the same as? That's the exact same behavior as what?
Ionization.
Energy of ionization, yes. That's because electronegativity has everything to do with something sort of like ionization.
The electronegativity value of an element indicates the attraction of an atom for shared electrons in a bond.
It's high for nonmetals. Fluorine is the highest. Why would that make sense? Look at this rule. What is the furthest right and furthest up?
Chlorine.
Fluorine. So it is the highest. What is electronegativity? What I should, before I answer that question though, what's the next nasty next to fluorine? We got two options, fluorine and oxygen, right? Oxygen, very common in biological molecules, does not play well with others. Very high electronegativity. Nitrogen's right next to it, but it's a significant drop down. But it is also fairly high with its electronegativity. So, let's learn about what electronegativity actually is. We know that it increases and decreases in the same way as energy of ionization, right? Once again, here we go. So here's our electronegativity. 4.0 for fluorine, 3.0 for chlorine, 3.5 for oxygen, 3.0 for nitrogen. All the way down here, what's the lowest left and bottom left? The lowest one, 0.7. Hydrogen has a nice little 2.1. Now, what are you going to do with these numbers? These numbers give you the relative ratio with which an atom is going to hold on to its electrons. So, if you're grouping hydrogen that has a strength, if you will, of 2.1, and you're pairing it up with the fluorine that has a strength of 4.0, who's going to win in that arm wrestling match? Fluorine's going to win every freaking time. Right? That's what electronegativity is. If you're dealing with, say, a carbon and a hydrogen, 2.1 to 2.5, is that going to be more of an even match? Carbon's going to win, but he's not going to blow the other guy out of the water, right? Carbon and hydrogen bonds are relatively equally paired. If you were to look at where the electron is between a carbon and a hydrogen, it's going to be right about in the middle. That's a gross oversimplification, but it works for illustration. All right? But if you were going to look at where a hydrogen is between a hydrogen and a fluorine atom, where's it going to be? It's going to be really close to the fluorine, because fluorine will grab that electron and hold on to it really strongly. And the hydrogen just can't keep up. So, what this does is it creates polarity of bonds. Now, if you have two hydrogens pairing with each other, this is not polar. Because the electrons are shared perfectly equally. Because one hydrogen ion has exactly the same electronegativity as another hydrogen ion. But if you pair that hydrogen with chlorine, which had a strength of what? 3.0? Not quite as much as oxygen, the same as nitrogen, right? That means that that electron is going to spend a lot more time, it's going to be a lot closer to that chlorine than it is to the hydrogen. Why do we care? What does an electron bring with it? That we've been counting over and over today. A negative charge, right? And if that negative charge is hovering perfectly in the middle between two positive charges, then it doesn't matter. But if that negative charge is hovering around the chlorine a lot more than it is the hydrogen, then that means that even though this is a covalent bond, most of that negative charge is actually going to be on the chlorine. And so that means that the hydrogen is going to have a lot less of that negative charge, which makes it kind of what? Positive. This gives us polarity. So even though it is not an ionic bond, it is acting kind of like an ionic bond. Because we have a positive and negative charge here. Not a full charge. It's not full plus 1 and full minus 1. It's less than that. But it is there. And what do we know about positive and negative charges? They attract to each other. Now these two right here, they're already attracted to each other. They're sharing electrons, if somewhat unfairly. But that negative chlorine, is it going to maybe feel like it's being, like it could hang out with a few other slightly positively charged hydrogens? Because the chlorine's a little negative and those hydrogens, they're a little positive, and so maybe you could hang out with them too? Because positive and negative charges are attract, right? Nonpolar covalent bonds are bonds that occur between atoms where they have an equal electronegativity. So a nitrogen bond right there is going to be nonpolar because it shares it evenly. A chlorine-bromide bond is going to be not very polar, not polar at all, 0.2, nonpolar covalent. Hydrogen-silicon, 2.1 to 1.8, not much of a difference, pretty much nonpolar. We get up to 0.5 or above as a good rule of thumb. A difference, so if we get oxygen and chlorine, 0.5, this is polar. Who's going to be more negative here? Oxygen has a 3.5, chlorine has a 3. Who's holding on to it tighter? Oxygen, because its electronegativity is higher. So that's polar. The oxygen's going to be a little bit negative, and the chlorine's going to be a little bit positive. Oxygen, sulfur. Oxygen's 3.5, sulfur's 2.5. Oxygen's going to be quite a bit more negative. Sulfur's going to be quite a bit more positive. As these bonds, as we get bonds between atoms that are more and more different in their electronegativity, we start creating polar covalent bonds. Those polar bonds create what we call a dipole. Polar bonds, dipole. Why do we call it a dipole? You ever seen a magnet with a north pole that didn't have a south pole?
Not very good one.
Next time you break a magnet, try this. It's one of those things that they tell you, but it's hard to actually discover it until you discover it and then forget. It's like, wait, why is it? Take a magnet and break it. And now try and force that magnet back together again. Like, oh, I just broke my pencil. I could glue it back together, right? You take a magnet, perfectly happy being a magnet, right? Sticking out, here's your north pole, here's your south pole. You break that thing in half, you try and glue it back together again, it's not going to work. Because the moment you broke that magnet, you just created a new north and a new south pole. And they are aligned with each other. You will not get those two magnets back together again. Every polar object, by definition, is going to have a positive and negative side. You can't have a positive end without a negative end. That's what a dipole is. Two poles. One of them positive, one of them negative. Why does it matter? Because positive and negative forces attract, right? And negative negatives repel, positive positives repel. We can draw an arrow that points from the positive to the negative end, just as a general rule of thumb of association, so that we can show which one is more electronegative, if we want to. Ionic bonds occur between metal and non-metal ions. It's a result of electron transfer. Why is that electron transferring? What's the electronegative difference between chlorine and potassium? Chlorine's 3.0, potassium's 0.8. Why is it that our ionic compounds was always an association between a metal and a non-metal? When we're talking about lithium, sodium, potassium, they want to give up an electron, right, to fill that outer shell. That's true, if we want to anthropomorphize a little bit. But it's not really that they're giving it up. They're associating with something else like a chlorine atom, and that chlorine atom is just quite literally ripping away their electron. Instead of sharing it together, it is sticking to that electronegative guy so hard that it loses connection with the guy that it came from. Oxygen, fluorine, chlorine, these really electronegative guys over here on the top right, they are literally stealing electrons from these metals because of the difference in their electronegativity, creating ionic instead of covalent bonds. So, rule of thumb, if the electronegativity difference is less than 0.5, so 0 and 0.4, it's nonpolar covalent. Yeah, it might favor one side or the other, but not enough to really create a strong dipole. If it's between 0.5 and 1.8, it is covalent but polar. If it's 1.9 to 3.3 or higher, the bond is ionic. One of them is pulling so strong that it just rips it right away. Yeah, I've just got 30 left.
We should just start talking about this.
Oh, really?
You should do it, guys.
80%
Math, go
though,
ahead.
80% math.
Yeah, that's true.
Like, what's important about this chapter 6? Is it more towards the end?
Well, I mean, there's going to be questions from every section.
I figured. You think it's more
Where were we
complicated?
at, 80 something? 88? Let's see where we get. So here's your rule of thumb. So remember when I said, is there going to be math on this one? Basic. This is addition, subtraction, right? But there could be questions like, find the polar covalent bond out of this list. Some of which you could rule out pretty easy, based on where they're located, right? In order to be polar, what do you need? You need a covalent bond between something kind of on the left, something kind of on the right. So is a fluorine bonded with a chlorine going to be a polar bond? No.
Wait, what?
Fluorine bonded with a chlorine? You can actually do the math. What is it? 3 and 3.5? I guess that would technically be right at 0.5, wouldn't it be?
Wait,
We go all the way back to here.
how'd you get 3.5?
4 and 3.5, or 4 and 3, fluorine bonded with a chlorine. That would actually be a 1. So yeah, it'd be polar. It'd be a polar covalent, right?
Well, if it was fluorine and oxygen,
Fluorine and oxygen would also be
that would be.
0.5.
Why'd you say it was?
Like these guys here. What if we did a phosphorus and arsenic?
No.
No. What if we did one of these and one of these? That's not even polar anymore. That's what? Ionic. So here's that difference. Here's your dipole. Here's what we have when our electronegativity is shared evenly between our nuclei. Here's what happens when it's shared unevenly. The majority of that negative charge is around one of those nuclei, which is what creates our negative pole and our positive pole. But if it's so strong that it just rips it completely away, it's not a polar covalent anymore now, it's just ionic. So here's a table of a few bonds, doing the math for you. Non-polar covalent, polar covalent versus ionic. But it's all just using those benchmarks that they gave you in that earlier slide, right? Basic math. Which category does it fall into? All right, shapes. Yeah, technically I've got 15 minutes, right? 8:55. Let's see if we can get through shapes. All right, remember before we had that space fill with the ball, with the thing down, with all 4 little white dots, right? So, here's our Lewis structure for that methane. It has a tetrahedral structure where every hydrogen is separated by a bond angle of 109 degrees. We can actually get a little bit further than that if we wanted to. It's fairly specific, but 109 is close enough. 109 degrees between every hydrogen surrounding that carbon. All X, Y, 4 bonds, where we're dealing with single bonds, are going to form that tetrahedral shape. Everybody follow? X, Y, 4. If it's single bonds, X, Y, 4, where it's all bond. Now, here's the reason why I say if it's single bonds. X, Y, 4. That works if it's this. Right? But you could also get this. That would also be XY4. Right? There's 1 X and 4 Ys. That would not be tetrahedral.
Wait, is that a Y or a 4 that you wrote below that X on the middle one? No, that. Is that a Y? Okay.
Yeah, they almost look like sigmas, don't they? Because I'm doing it fast. These shapes only work if we're talking about shapes around a central atom. Alright? So when we're talking about the shape of these molecules for this chapter, we're not going to get into something like this, where it's all sorts of hokey weird. Every other shape is going to be a variation of this, though. But it's not going to look like that, but I want you to appreciate that it is that. It's just missing one end. So the goal for this section is learn to predict the 3-dimensional structure of a molecule. What shape is it going to be? And this leads us to the super valence shell electron pair repulsion theory. That's a really long name and a really hard to remember acronym. Hard to remember a word that we use to abbreviate something. And pretty much all it says is the reason why these things spread out is because those electrons in that valence shell, they are all negatively charged. They want to spread out so that they are as far away from each other as possible. Thing is, those pairs have to stick together because they're involved in covalent bonds. So the pairs stick together. But that means that those 4 pairs want to be as far apart from each other as possible. And in a sphere, that means that they will be 109 degrees away from each other every time. Unless, of course, you start adding in double bonds. If we add in double bonds, that means 2 pairs have to be close to each other, right? Because they're in a double bond. So now what's our bond angle between those 2 oxygens? 180 degrees, perfect line. Because, why? These guys right here are locked in place because of the double bond. So what's it going to do to everything else? Push it as far away as possible. And when you're dealing with electrons on both ends, that means that it's all the way out there, spread out like you're trying to spread eagle or spread your arms as far as you can. Linear. So, if we are dealing with double bonds, the shape of the molecule with respect to that double bond is going to be linear. The carbon and the oxygen in this case are directly apart from each other. Straight line, linear. And the other oxygen is all the way on the other side. Can you take this lesson and apply it a little bit further? Remember that HCCH, C triple bond CH? What's the, I mean, I kind of showed you when I drew it, but what's the shape of that molecule? Triple bonds are even more rigid than double bonds. So what do you think the shape of that molecule is going to be? All that negativity on one side, what's going to happen to the hydrogen? Is it going to be off like at an angle? It's going to be as far away from all that negativity as possible, right? Which means it's just going to be a straight line. Just like this. All right. If we add a double bond and two single bonds, instead of 109, what's happening? We have 120. And this is planar. Why? Those two pairs have to stay right there, right? But that means that the electronegativity around this bond right here and around that bond right there, both of them need to be pushed as far away from everything as possible. So why wouldn't it be up here? Because that would put it too close to this guy, right? To all of this stuff right there. So it's going to be shoved down. And if it gets anywhere, like this is on the plane of the board right here. Everybody follow? If this guy right here pulls a little bit out in front of the board, it's getting too close. It's putting too much pressure. It's getting too close to some of that other negativity. If it goes behind the board, it's getting too close to that negativity. And it's certainly not going to pull up like this, right? Or it's not going to go down like that. We're not going to pinch these two guys together because now they're too close to each other, right? It's not going to do this. Because there's negativity here and negativity here. Just like there's a lot of negativity there. The electron repulsion theory is what is used to describe why these small, simple molecules take the shape that they do. It's all because of that negative, the repulsion, the negative repulsion of those electrons. So, why is this sulfur dioxide molecule also planar? With that same 120-degree angle. It has a lone pair right here, right? And that lone pair has the same electron density as that right there. Because that line is just a pair of electrons, right? So if we looked at this as pairs of electrons, we have a double pair here and two single pair. It's exactly like this. A double pair here and two single pair. So this has the same shape, it's just missing that third guy. It's an invisible guy because it's just the electron pair right there. Everything is about getting that electron density as far away from each other as possible. So what's the shape of our CH4? Tetrahedral. 109 degrees. Now, I want you to appreciate something. If I take these two little white balls right here, and I force them to squeeze together, that is going to bring a lot of electron density right there. But what does that also mean about this 109-degree angle right here?
Spread out.
They have room to spread out, right? Because I just took these two guys right here and squeezed them together. I moved them closer to each other. By pinching those two white balls, these two guys can spread out from 109 to 120. Because that's what a double bond is. It's forcing those two bonds right there closer together.
Thank you.
For the sound effect? Or for
No, you want us to appreciate it, and I did.
Oh, okay. Sure. Trigonal pyramid versus tetrahedral. What's the difference? What's missing in that trigonal pyramid? That top ball up there, right? But it's not because it's not there. The electron density is still there. It's just invisible. It's that lone pair on that nitrogen, right?
The eye of horns.
Sorry, don't see it.
Top of a dollar bill.
Oh, yes, okay.
The Illuminati thing?
Yes, the Illuminati, yes. I apologize. Totally different thing, but yes, that's what he was talking about. What's the bond angle between those guys going to be? It tells you up here, but even if you didn't look at it, you'd be able to tell me, right? You should know. 109, because it's the same thing as the tetrahedral, it's just that that top ball is invisible, right? But the electron density is the same, and so the bond angle is going to be the same, right? So why does water look the way it does? This is that same tetrahedral shape. Except instead of one invisible ball, now we have two. What's that bond angle going to be between those two hydrogens? It tells you on the slide, but you should know it. 109. Everything is bent 109. As everything's single bonds or lone pairs, it's always 109. The only thing that changes that is when we start adding in double bonds and triple bonds. Then things can bend as far out as 180, right? A triple bond, that puts you at 180. Or two double bonds on either side, that's 182.
And only when it's single bent, it's 109. Like bent shape, 109. Bent wedge stash, 109. But
Yeah, all of the angles, like the angle between these two hydrogens is 109. The angle between that hydrogen right here
yeah.
and the pair up here is also 109.
Oh, that's gonna be.
Everything is 109.
What's the 120 thing?
The 120, well, everything in the tetrahedral is 109. The 120 happens when we get the double bond. We take two of those things and we bend them closer than 109.
Okay.
And that gives the other guys room to spread out to 120.
And that's only if it is.
That's only if there is a double bond.
Okay.
And two single bonds.
The double bond is always gonna be like 120.
A double bond will give you a 120-degree angle between all of the bonds.
Okay.
But then two single bonds is 120 as well, right?
Two single bond with a double bond out, yeah, it's 120.
Always 120?
Well, here's the thing. What's 120 times 3? 360.
So no.
Because it's a planar circle, right? So the bond angle between those two single bonds is 120. And the bond angle between any single bond and the double bond is 120.
So it's 120.
Right. Because literally those two bonds, it's not even that they're squeezed next to each other, they are literally on top of each other.
But to count the whole would be like 360 if it were.
Right. But the only reason it works that way, because if you 109 times 4 is not 360,
No.
but that's because we're not talking about a plane anymore, now we're talking about a sphere. And so you have to draw a plane, which is why you have 4 planes here.
Okay.
The 4 sides.
So whenever it's
This-
109, we're always dealing with a plane. Is that what you're saying?
When there's a double bond, everything is on the same plane.
Okay.
When it's a single bond, you are talking about the plane in between two angles, but every bond is going to be on a different plane with respect to another bond.
Okay.
It works like this. If you take your two fingers, spread out your fingers as much as you can, and then shove them together in a really inappropriate gesture. Because that's the bond angle.
Okay.
Two of them are going to go up and down, up above the plane and down below the plane, and two of them will be right on the plane.
We're not gonna forget that.
Not going to forget that metaphor, are ya? I didn't tell you what inappropriate gesture it was. You filled in that detail. I just kind of like showed you where the gutter was and let you jump in. Anyway,
Yes, we're done.
Okay, electron groups. Yeah, that's pretty much talking about the same thing.
Good way to end.
Prediction. And then we're there. All right, good. So we're not going to finish this. Oh, so that means that this test will not have chapter 6.
I'm scared of that.
Or do you want to finish?
No.
No?
No.
I mean, just
We just say you put it on the test and whether it gets.
what are we at? How many's left?
Just like
Three slides? 4, 5, 6, 7.
15.
On dipole. Yeah, that's quite a. That's
It's just 6.9.
just 6.9, but that's quite a
Just
bit.
put it on the test. Put everything but 6.9. It'll be fine.
No, see, that's not what I'm doing. I'm not going to put everything but 6.9. not gonna do
Just
that.
put it all, just put it all on test.
Unimportant.
Just figure it out.
We would have forgotten you.
How about just leave chapter 6 off and we'll promise you that we learned it?
No. I'm willing to put chapter 6 on without finishing it if you all
Yeah.
agree to it.
Do it.
but-
You
Yeah.
please do.
I like
that.
Just put 4 hours.
Well, we had 2 people leave, so.
Okay, but if we take a vote, we all vote yes, so we outvoted them anyway.
Yes.
Well, they're just not committed.
Can we take a
Does-
vote?
Does everybody here say we want chapter 6?
Yes.
Yes.
Show of hands. 'cause
Get
I
it
don't-
over with.
So we all,
I don't
chapter
want
6?
that.
Get it over with. I don't want to do
Oh,
it
okay,
again.
awesome.
Or you can just stay here and teach it and he'll record it and then we'll
That works too, I guess.
Yeah.
Yeah, if you wanna keep lecturing, I'll put it up.
No,
Yeah.
I'm okay with putting 6 on there.
Like you're
because
doing empty classes.
the likelihood that you'll get a question over chapter 6, over section 1, 6, 9 is low. But it is gonna be your responsibility to know if I have it on the test, I'm not gonna feel bad, because everybody between you all are here.
I'm
You
willing,
just give us like 3 hours though?
I'm willing to take that risk.
One more hour? 2.5.
2.5 hours.
15 more minutes.
30 minutes.
Kelly.
We ain't winning that one.
That's
Remember
okay,
how
though,
cool it
guys.
was where
This
they
is,
showed the
I have a
professor
4-year-old son
and
and a
a
9-year-old
couple of
daughter.
ducks
This is
had
not hard. I can sit
recorders.
there all day.
And then a few weeks later, it was all recorders, and then a few weeks after that, the professor had just left a player playing all the recorders.
That was in a movie?
Yeah.
That sounds familiar, yes, where the whole class is just the professor playing and recording and all the students are recording the recording so that nobody ever goes to class. Yeah. Which, if I was really interested in doing it and had the backing, I could totally do, just record myself teaching this class once, and then just post the videos every time, and then just let the computers do all the grading. And then all I would have to do is sit back and answer you guys' questions when you get confused about individual topics.
Do it.
Because that would make you feel great as a student, right?
Yes.
That's the flipped classroom model. It's beautiful.
So
Yeah,
it's
except
going
that there
on-
would
so
never be a flipped class in that
Chapter
situation.
6 is going on there,
Wait, what do you
correct?
mean?
Sure.
Oh, sure. Are you going over this now? Because I will stay.
Do it. Post
I
it.
could.
Because I'm here for it. I
I cannot force you to stay. But I can keep talking if you're still here.
I'll keep talking.
don't. Keep talking about it because I'm here for this. And I need to know this.
So the whole. It's actually recording. Yeah, it's still going. They haven't like run out of space because I talked for 3 hours, 3 minutes.
Oh, the lens cap's on. I'm kidding, there's no lens cap.
Alright, so the point of 6.9 is to figure out the polarity of a molecule. So, you should already be able to tell me, before you even get into this, water, is it polar or not?
Yes. Polar.
Why? There's 2 reasons why water is polar. One of them should be really obvious, and the other one should be really obvious for different reasons.
It's got those empty balls on top.
That's one reason. One side of that tetrahedral, right, is going to be nothing but negative electrons. There's no other positive charges on that side, right? And what's the other side? What's the reason why the other side, where the hydrogens are, why is that going to be polar too? Because what does oxygen do when it's sharing an electron with almost anything else?
Well,
It holds on to it really strong, right? Because it's very electronegative. So not only is one side going to be really negative because there's nothing but electrons, the oxygen itself, the center, is going to be pretty negative because it really holds on to electrons, and that leaves just those 2 hydrogens hanging out on the other side to give us a little bit of a positive, right? So water is polar, but the way we just answered that question is the whole point of 6.9. Of appreciating what shape does. Where are the negative charges? Can we draw a line or point to a way in which this side is kind of positive and this side is kind of negative, and if we can, then it's polar. If we can't, then it's not. So, for example, this carbon right here and these chlorines. Chlorine
is rather electronegative. Carbon is rather not. So where's most of the electron density going to be? Around those chlorines, right? But is it still evenly distributed everywhere? Is there a side of this molecule that is more negative than the other side? No, because all of these chlorines are pulling electrons away from that carbon equally, right? And in every direction. So is this a polar? Can we draw a side that's positive and a side that's negative? Nope. So this right here, the 4 carbon chlorine dipoles, because remember a dipole is any situation where we are creating poles, right? We do have an uneven attraction between the carbon and the chlorine, which does create a dipole. But there's 4 of them, equal, all pointing out in every direction, so not polar. There, 6-9 done. Just kidding. Is this molecule polar or not?
Which one?
This one right here, carbon dioxide. Carbon and oxygen. Oxygen is more electronegative than carbon, so it will create a dipole, right? Because anytime we have electronegative, an uneven electronegativity, it creates a dipole. Even if it's a tiny one, a little bit positive and a little bit negative.
I'm going to say no because it says CO2 is a non-polar molecule.
Yeah, exactly. You can cheat if you just read the slide. But the point is to think about it. We're creating a dipole here, right? But we are also creating a dipole of exactly the same intensity pointing in the opposite direction. So what's -4 plus +4? 0. What's -0.4 plus +0.4? 0. So this is also non-polar, because even though there is electronegativity between oxygen and carbon, they cancel out. Non-polar.
Does that last one be 0.0?
0.0?
-4, -0.4,
Negative 0.4 and positive 0.4?
Uh-huh.
Yeah, well, sure, yes. 0.0 for where we're about significant figures. Sure. So, what are we comparing here? We're comparing shapes. This is a linear molecule, right? This is a tetrahedral molecule, right? Now, could we change this molecule and make it into something that was polar? What would we need to do?
CO2?
Well, let's not mess with CO2, but we could do it there too. What would we do to this carbon tetrachloride to make it polar? Change one thing.
Put a hydrogen instead of chlorine?
Yeah, take that chlorine right there and make it hydrogen. Carbon is now more electronegative than hydrogen by a little bit. And so that means that that dipole right there, that arrow, is going to switch directions. And so now that hydrogen is going to be a little bit positive, right? And all these chlorines down here are going to be more than a little bit negative, right? Would that be polar? Yes. Because we have a positive end and a negative end.
Every time you say that, I'm thinking country and rock and roll.
Okay?
A little bit country, a little bit rock and roll.
Very good. Polar molecules, like hydrogen chloride, are polar because there is an uneven dipole. Anytime you're talking about a single bond, if there is a single dipole, if that electronegativity is different by more than 0.4, then it's polar. By definition, remember? Because how did we define whether or not we were dealing with something polar before? It was literally subtract the electronegativity values, and if it's 0.4 or less, it's non-polar. 0.4 to, what was it, 1.8? Was polar covalent, and over 1.8 was ionic. Right? So anytime you're talking about a single bond, if the electronegativity is more than 0.4, if the difference in electronegativity is more than 0.4, it's going to be polar. But the question is not whether or not this is polar, because that's easy to calculate. The question is a larger molecule polar? Like this tetrahedral molecule, is that polar? Well, in this particular case, carbon tetrachloride, no, it's not, because there are dipoles, there's 4 dipoles, but they're all pointed in directions and they cancel each other out.
There is a dipole here with carbon dioxide, but they're pointing in opposite directions, so they cancel each other out. Water. We have a dipole that's pointing towards the oxygen, a dipole that's pointing towards the oxygen, and then just a whole bunch of negativity on this side over here. Could we draw a line, like right here, that we could then define as a negative side and a positive side? If we drew a line right there between the hydrogens and the oxygens, if the oxygen is keeping most of the negativity from those bonds, then that leaves these hydrogens as slightly positive, right? It leaves the oxygen as more than slightly negative, which means now we have a positive end down here and a negative end up here. These dipoles do not cancel out. They are in fact additive. They're both adding to the oxygen, and so therefore H2O is polar. Get a strong magnet and hold it up to a stream of water. It'll move. Because charged things respond to magnetic fields. Polar things respond to magnetic fields. Now, that's not to say that you'd be able to use a magnet test to determine whether or not a test question is polar. You'd actually have to do the math and think about the shape.
So it would be the water with the magnet, or would it be the things in the water?
The water with the magnet. Water
Okay,
itself.
water.
Pure water.
Okay.
Because water is polar. And therefore it has a positive and negative side. And things with positive and negative charges react to magnetic fields. That's outside the box for this chapter.
I
but-
just think about like a blow dryer in the water and how it's not necessarily the water, it's.
Right. No, that's a very different thing between conducting electricity, which pure water is bad at, but regular water with a whole bunch of crap in it is really good at, right? But that's a totally different thing from polarity of the molecule of water itself, which is what we're talking about here. So, this nitrogen, is that polar or not? Try to not read it. Tell me if you can answer it. Nitrogen with 3 bonds of hydrogen, so we have an ammonia. Hydrogen and nitrogen, are they significantly different with electronegativity? A little bit different. So yeah, we're going to have a dipole. We have that lone electron pair on one end that's going to be a nice placeholder for a whole bunch of electronegativity as well. Since all of these guys are pointing at the nitrogen, does that mean that this is polar? Yes. We could draw a line that says the nitrogen is very negative and the hydrogens are very positive, right? Or slightly positive at least, each. So therefore, it is polar. The dipoles do not cancel out, therefore it's polar. Oxygen fluoride, is it polar or non-polar? Oxygen difluoride, actually. So, how do we do this? Oxygen has an electronegativity of 3.5, fluorine has an electronegativity of 4.0. So the difference in electronegativity is 0.5. So is the individual bond polar?
Yes.
Yes, because it is more than 0.4, right? Which direction is it going? Where is the electron density going? Who has more?
Towards the fluorine.
What's
Right.
more than 0.4?
The difference between oxygen and fluorine here, 3.5, 4.0 minus 3.5 is 0.5.
Oh, 0.4. I
Or 4.0, 3.5.
I
The
had
answer
in
is-
my head that it was bigger than 4, and I was like, how could that be?
Right, yes. So, the difference here is 0.5, which is therefore larger than 0.4, which is the cutoff for nonpolar, right? Up to 0.4, it's nonpolar.
Okay, so up to 0.4 it's not, but everything over 4.
0.5 to 1.8 is polar.
So,
Over that is ionic. Which means now we're not even talking about a covalent bond anymore, we're talking about, like, completely grabs it. Right? So, 0.5, the direct, yes, it is the electronegativity, the dipole is going towards fluorine because fluorine, oxygen is nasty, but fluorine is worse.
So fluorine's actually pulling those electrons away from oxygen, which I'm sure pisses it off. But it can deal, because it's mean to everybody else most of the time. What's the shape of that going to be? We can draw the Lewis structure here, where we have this planar, triangular molecule, right? Where our dipoles are pointing away from the oxygen, both of them are pointing away. So is this polar or not? It is polar, because both of them are pointing away. They do not cancel out. Now, why is this a triangular molecule instead of linear? This is a question that refers you back to earlier things. Because there's no double bond. Fluorine, how many electrons does it need to share to fill up its shell?
Just one.
Just one. Which means it's not going to form a double bond with oxygen, it's going to form a single bond. Which means that those two pairs out there are by themselves. So it's not linear because there's no double bond. What's the bond angle between these two fluorines? Tell me.
109.
109. If there's no double bond, the bond angle is 109.
What? Sorry, I'm so zoned. Where is the 7th valence on the fluorine?
Fluorine has, well, here, it's in that line. That line represents two electrons, one from fluorine, one from oxygen.
Okay, got it. Thank you.
Good question. Ionic bonds are the strongest of the attractive forces found in compounds. Thus, most ionic bonds are solid at room temperature. Sodium chloride does not melt until 801 degrees Celsius.
Salt baths are nice.
Right, that's the irony, is that ionic bonds are incredibly strong as crystals, but they're incredibly weak in an aqueous solution. Because, tell me why. This is outside of the box. Tell me why.
Because water's polar and it breaks down the ionic bonds.
What is an ionic bond? It's an attraction between two opposite charges, right? Does water, being polar, have a positive charge that could attract the negative charge of chlorine? Yes. Does it have a negative charge that could attract the positive charge of sodium?
Yes.
Yes. So when you take a salt crystal that takes 101 degrees Celsius to melt, and you put it in room temp, like cold freaking water, 0 degrees, liquid water, what's going to happen to that salt crystal? Gone. Because water will rip it apart. Because there's a lot more water than there is salt.
And the irony is it lowers the boil point of water.
Yes. Which allows, it also changes the freezing point as well. So that would change the temperature at which it could be, so you could actually get water that's below the freezing point of water because it's salt water, which would still rip more salt apart.
Will it?
Yeah, up until you get to a point where you're saturated with salt, at which point it won't because there's no more room for entropy to take over and pay for it.
And it does it much more slowly, does it not?
All reactions would run slower, yes, but it would still do it. All right, so dipole-dipole interactions. A dipole is simply where you take a polar, anything where there is an unequal electronegativity creates a dipole, right? Anything where that electronegativity is 0.5 to 1.8, it makes a dipole. A positive side and a negative side. We've talked about the attractions between those positives and negatives, right? So, dipole-dipole interactions are inter, very important difference. That's why I had to think about it for a second. Inter means between two different things, right? Intra means within the same thing. And you can still get intramolecular interactions from dipoles too. That's what all of proteins and nucleic acids are built on, but we'll get to that later.
intermolecular interactions, if you create this dipole between two hydrogen chloride molecules, which can't be in an aqueous solution because then they would have just, but forget about that for a second. So if you have this hydrogen chloride dipole, that negative chloride side is going to be attracted to the positive hydrogen side of another molecule. How strong is that attraction going to be? Kind of weak. Much weaker than the attraction between these two guys, right? But it's going to be there. And the stronger the dipole, the stronger that dipole-dipole attraction, right? Just like the stronger the magnet, the harder it is to get it off your fridge. I got some of those really super strong rare earth magnets. I love them. I put them on my fridge. One of the best reasons why I love them is because I have absolutely no fear that my son will accidentally swallow one. Because if you want to get those suckers off the fridge, you gotta really try.
Put them on a piece of paper and then fold the paper to the edge.
Don't break the fantasy! My son is not that smart.
They actually feed cattle magnets, so that as they're grazing, and they pick up bits of wire and nails.
Just, yeah, to keep it in that one stomach so it doesn't go any deeper.
Right, and so
Yeah.
when they butcher, they take out the magnet, they clean it off, and they feed it to another cow.
That is
Thank you.
That's hilarious.
So here's the thing. Dipole-dipole interaction is the attraction between the positive side of one dipole and the negative side of another dipole in another molecule. Or in a really distant part of the same one. But for our purposes with these really simple things, another molecule. There is a special type of dipole-dipole interaction, not because it is necessarily the strongest, but because it is the most ubiquitous. And that is called hydrogen bonds. A dipole interaction that involves a hydrogen ion as the positive side is a specific type of dipole interaction that gets a specific name called a hydrogen bond. And it is important because that dipole interaction, that guy, it's not that guy, that's unfair, that's between nitrogen, that guy! The dipole interaction between hydrogen and oxygen of other water molecules is the reason we are here today from a naturalistic standpoint. Because remember that weird thing that water does, where as it freezes, it gets less dense, and therefore it floats, thus protecting liquid water beneath it? The entire reason that happens is because of that hydrogen bond. That dipole-dipole interaction is strong enough to fight gravity. Have you guys ever seen the movie Bug's Life?
Mm-hmm.
There's a really neat thing in there where it's one of those like, ooh, I love it when animators actually understand science a little bit. There's a thing where they're like, he walks into the bar, right? And the barkeep's like, he'll have a drink, and so the barkeep gives him a water, but he doesn't give it to him in a glass. What does he do?
He's gonna drop.
He just goes, whoop, here, take this. And he's holding the drop in his hand like it's just a big ball of pizza, and when he wants some, he just sucks on it, right? Why doesn't the water just whoosh? Because if you tried to hold a ball of water that was appropriately the same size, it would not just whoop, sit in your hand like it's oh so nice. What would it do?
Surface tension.
Whoosh, surface tension. Strong enough to keep water skipper spiders, they can stand on water without getting wet. Because they're literally stepping on water and they're spreading out their weight far enough that the surface tension of water will hold them up. They don't get wet. What is surface tension? Hydrogen bonds. The surface tension of water is due entirely to the hydrogen bonding, the dipole-dipole interaction of different molecules of water. And it's everywhere in the water. Everywhere! Except for right at the top, all of those hydrogen bonds can only point to other water molecules, which means they're pointing to the side and they're pointing down, which makes the surface of water get just that much stronger.
So it's like when you take cornstarch in water and you can walk across it, do stuff.
Well, that's
It's non-Newtonian fluids. It's sort of like, that's a good metaphor for it, yes. But it's for a totally different reason. But it's a good metaphor for it, yes. The big pools of cornstarch, where you can, if you move quickly, you can run across it.
Yeah.
It's a metaphor for how spiders stay on top of water. Totally different reasons. So, hydrogen bonds always involve a hydrogen and something else. usually an oxygen or a nitrogen or sometimes a fluorine. But in biological molecules, it's nitrogen and oxygen.
The first, honey, I did something that should get me jailed to the kids, or the book on which it was based, the young boy got trapped inside of a water droplet.
For Honey, I Shrunk the Kids?
Yeah,
Yeah.
that or the book it was based on.
Okay.
And they had to figure out how to pierce
Pierce,
the
yeah.
surface tension. Yeah.
Tiny little bit of soap. That's all it would take.
I think they had to use something physical.
Yeah, like a nail, something really sharp, yes. That would also sort of do it, but also sort of not, because if you push on the surface tension, all that's going to do is just create a new surface. Yeah, so it's just the water would bend around it, but the surface tension never really breaks. So it works for a story, but the science behind that actually breaks down.
The kid would drown first before they let him out if they're that small.
Right, but he would. But the other problem is if he's really that small, then he wouldn't actually drown, he would suffocate.
Yep.
Because when he opens his mouth, the tension of the water would be so high that it wouldn't actually enter his mouth.
Take a needle and a water droplet. Yes, it'll deform, but then it'll eventually pierce it.
But then it forms a new surface tension right at the border where it's holding onto the needle. Unless the needle is nonpolar, at which point it'll pierce it immediately and then the water never touches it. But the droplet itself, if you touch that droplet with a needle, the droplet won't go. But try this.
But it gives him a path out. He can get, if you get the needle.
Right, now, neater trick. Try that little drop of water, take your little needle, dip it in just a little bit of dish soap,
Yeah.
and then just touch the very top. Don't even try and pierce it, just touch it and watch that drop of water. Why? Because soap disrupts hydrogen bonds.
Would a little bit of alcohol do that as well, since it's invincible?
No, I don't think so. I think it'd have to be a non-polar substance.
I don't think we can say with Honey, I Shrunk the Kids, commented, so.
Right. What's a nice reference? Bugs Life, Honey, I Shrunk the Kids. This is why you stayed after class. Dispersion forces are neat. They're very, very weak interactions caused by temporary dipoles. Because here's the thing. When we're talking, and we're not really going to get any deeper than this, and I wish that we could, but it would take a much higher level chemistry course. But electrons aren't really things that have specific places. When we talk about understanding the shape of atoms, we are conceptualizing them in a metaphor that works great at really basic levels. But when you start getting into quantum stuff, you start talking about electron potential and electron density and all sorts of things that are really only represented by math. And so, because of that math, it means that electron density can shift around in the same way that the surface of water can shift around. And so even in an atom that is otherwise perfectly neutral, sometimes, for really brief femtoseconds, that electron density will happen to be more on one side than the other, creating a very brief temporary dipole where one side of the atom is a little negative and the other side of the atom is a little positive. And so these dispersion forces are very weak attractions from temporary dipoles, but they are what allow for non-polar molecules to form liquids and solids, to have weak attractive forces from each other where they're interacting with each other because of the way that they're pushing on everybody's electron density. But it's temporary. And why does all this matter? Because the melting point of a substance is dependent upon the attractive forces that keep it together. The reason that things are solid at room temperature is because the attractive forces between the atoms of that substance are strong enough to hold it in a rigid shape. So the more attractive forces we have, the more likely we are to be a solid at room temperature. The less attractive forces we have, the more likely we are to be a liquid at room temperature. Go even lower than that, and we might even be a gas at room temperature. Because the melting point of these substances is dependent on how strongly they are attracted to each other. So stronger attractive forces, like hydrogen bonding and ionic bonding, results in extremely strong lattice crystal structures. This is why water is less dense at 0 than it is at 4. Because as water freezes, it has to form a crystal structure. So that all of those negative and positive poles are pointed at each other. When it's a liquid, they can shift around each other and form and break and form and break and be just a liquid. But as ice, they've got to be... And that means the density is just a little bit lower. Which is why ice floats. Ionic bonds between magnesium and fluoride has a melting point of 1,248 degrees C. These guys down here, the only thing that holds them together between molecules is dispersion forces because they're nonpolar. So what form do these guys have at room temperature?
Gas.
Gas. Hydrogen bonding, melting point 0. Hydrogen bonding is strong enough to hold it together, so instead of being a gas at room temperature, it's a liquid at room temperature. Really, really strong ionic bonds, it's not even a liquid at room temperature, it's a solid. Ionic bonding and covalent bonding are strong. Hydrogen bonding, then dipole interactions, because that's just non-specific hydrogen bonding, right? And then dispersion forces in order of strength, so weakest down at the bottom, strongest at the top. And that's it.
Okay, just making sure. Hydrogen and dipole are both liquid at room temp?
No, well, hydrogen is liquid at room temp, but specifically water is liquid at room temperature, and ammonium is liquid at room temperature as well because it melts at -78. That's also hydrogen bonding. Dipole interactions, hydrogen iodide, hydrogen bromide, hydrogen chloride, they melt to be liquids, but when we get down to dispersions, and some of these are even gases, you get down to these dispersion forces alone and you're dealing with gases.
So I guess the low, okay, so it could vary with dipole with gas.
Right, because
and
a
other liquids.
dipole is just any interaction that's from a dipole, and dipoles are dependent upon what you're talking about, right? So hydrogen bonds are a specific type of bond where we know what one half of that bond is, hydrogen. But the strength of those hydrogen bonds can still vary, because the electronegativity between oxygen and hydrogen is different than between fluorine and hydrogen, right? And so, but it's still just a special type of dipole that we call hydrogen bonds, which tend to be strong. But you can have dipoles that are strong, you can have dipoles that are really, really weak. And so, the weaker the attraction, the weaker the interaction, the more likely it is to be a liquid or even maybe a gas. I am just a klutz today. It's because we're here too late.
Yeah.
So anyway, that's all of chapter 6.